graph neural network, social network analysis, and generative AI in education. Sir has supervised 4 PhD students, 15 MTech students, and currently he is supervising 5 PhD students and MTech students. Apart from this, Sir has published several journal articles, book chapters, and a Springer reference book, and has presented his research at leading international conferences. He is also widely recognized for his educational initiative through his YouTube channel CS Simplified and for developing a highly rated massive open online course on Python programming. Today he will be taking the theory session on convolutional neural network, foundation, architecture, and application. With this brief introduction, I extend a warm welcome to Dr. Mahipal Jadeja, sir, and I request you to kindly take over the session. Over to you, sir.
Thank you so much, ma'am. I would also like to thank Bhaskar sir for organizing this particular activity and also inviting me. So let me just try to share my screen. I request you to
Yes,
make
sir.
me a host or
Yes, sir.
co-host so that I can do it. Yeah.
Yes, sir. I am making
Meanwhile,
a
I will also
presentation.
try to join with one more device. Yeah, while you do so.
I'm making you presenter, sir.
Okay.
Yes, sir. Now you can present, sir.
Okay. Okay. Just a second. Okay, fine. So yes, now I can present. So yes. Okay, so my screen is visible. I can verify. Okay, so
Yes, sir. It is
let's.
visible.
So before I start, I would just like to know how much was covered with respect to deep learning part. If someone can summarize or just if you can give me some pointers so that I can discuss accordingly with respect to first day. You can write it in the nothing but our chat window also, so that it will help me to kind of fine tune my session. But in any case, we can start. So what I'm going to do now is first, instead of talking about foundational of deep learning aspects, because I assume that that has been already covered. What I'm going to do now is I will mainly focus on convolution. But before we directly jump into the ideas of convolution neural network, I have designed one activity. Let's just go through this particular activity just to motivate you. What's the significance of this particular important word, which is called nothing but convolution? And then we'll go into the depth of it, that how it's going to help us with respect to convolution and neural network. So this is again, I have launched this on my own website. So I will soon share the link of this with you so that you will be able to kind of do this particular interactive activity with me so that you can appreciate the idea of convolution first, and of course the other things which are relevant to convolution neural network. So let's start, right? So usually we Indians, we love cricket, so therefore I have started with this particular fun example of nothing but cricket speed gun. So what's the idea? That let's say we are having that we are just observing one beautiful match, and we would like to find out what is the speed of the ball, like with respect to ball, delivery, a particular delivery which is going bowled by a particular person or cricketer, I should say. And then let's say within a split seconds, we are going to have three different readings with respect to that particular single delivery. Now, what are the issues? Our gun is not up to the mark. It's slightly faulty. And now we would like to come up with the most, one should say, accurate speed based on our three readings. So let's say, let's consider this particular simplistic scenario where let's say, with respect to one particular delivery, we have got this three or five readings. And first three readings goes like this: 135, 137, and 139. So the last reading is 139. Second last reading is, I should say, 137. And the first reading, right, which we had taken, like the earlier reading, which was nothing but 135. Now, what is the idea of kind of coming up with the accurate, I should say, speed of this particular delivery. The core idea goes like this: that if we are having successive kind of readings, then the very last reading will have the most kind of impact on our overall prediction or guess. So therefore, ideally, what we should do, whatever reading we have kind of gathered towards the end of this particular experiment, which is in this particular case, let's say with respect to first degree, it's 139. So what we should do, as you can see in my weighted window, what I'm going to do, I'm going to give more weightage to that particular score because it's the recent one, and it's very likely that it's the actual speed of the ball, right? And the middle kind of reading will get, let's say, 0.3, 30% of importance. And the first kind of, I should say, the reading will get 15% of, let's say, kind of importance. And if you sum this up, then of course you will get nothing but one as the answer, that which makes sense. So this is so now what we are going to do? We are going to perform one simple operation. I'm going to multiply this last reading 139 with 0.55. Then I'm going to consider the second one. So basically, it's nothing but weighted average, I can say. So then 137, I am going to multiply it with zero point 0.3 because importance of that particular reading is 30% only. And importance of the very first reading is just 15%. And basically, I will perform this particular operation. So as you can see, 0.15 times 135 plus zero point 0.3 times 137 plus 0.50, 0.55 times 139. And then I got this particular estimated speed. So this is the very likely speed of the very first ball, right? And now what we'll do in the next iteration. So let me just go to the second iteration. So in the second iteration, let's say we go like this. Let's say this three are readings. Then again we'll repeat this. But you can see that here consecutively. So instead of let me try to make more sense. So instead of, let's say, this kind of cricket balls, assuming that I am trying to estimate speed of car, right? And then these are consecutive readings which I have taken with respect to one particular lane. So now in the first iteration, I did the similar thing, but now I have not, I have more than three kind of, I should say, readings. So what I will do, I will change my window position. So as you can see, in next time, instead of considering first, I should say 3 points, I'm going to consider the next 3 points, right? So let me just try to go back to the original example so that we can hopefully it will work. Otherwise, I will just change the kind of page and go back to it. Let me just try to kind of come back over here, or maybe I will click on play button, then it should work. So as you can see, now the window is moving, right? So it's sliding towards the right. So in the second, so in between, if let me try to pause. So you can see now window is somewhere else, not in the beginning. So every time we are going to just move this particular window one position right, and we will repeat this particular process. So this is called nothing but 1D convolution. It's very kind of intuitive, right? So basically what we are doing for a series of, I should say, readings, we are just doing weighted sum with respect to some specific window size, right? We are not going to consider all the kind of readings in one go, but we are considering some relevant readings in one shot. And of course, these are you can argue and say why we have fixed this particular window size to three only. We can go for, let's say, 4 or 5. Of course, we'll come to those things very soon. All these are, I should say, hyperparameters. Hyperparameters means parameters which we can decide. So there is no fixed rule that my particular window size is series of, I should say, the number of nothing but kind of observations which I'm going to consider in one particular iteration. So for that particular number is three as of now, but you can say you can ask why not we are going for 2 or 5. Right? So of course we can take different values with respect to that particular window size, and it will have some impact on our outcome. And we'll talk about it later when we actually take one practical problem and apply convolution over there. But for now, my objective is just to motivate you. What's the fundamental idea behind this interesting operation, which is called nothing but convolution, at least in the context of 1D, right? So hopefully the idea is clear. I'm also sharing this particular link with you. So in case if you would like to kind of go through it simultaneously with me, you can do it. As per my kind of verification, this thing will work on your system also, as well as your on your cell phone also. So let me just try to share the link of this with you. So hopefully I'm audible, right? Someone is saying I'm not audible. Can anyone confirm?
Yes, sir, you are
Yes,
audible.
sir.
Yes, sir. You are audible.
Okay, 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 fine. Thank you. So now let's just go through the other examples, and then it will make more sense why we are learning all this and how what will be the impact of these things, especially with respect to nothing but when we talk about deep learning on convolution neural network, we usually talk about nothing but image processing. So why all these things are associated and how all these things are associated with nothing but ideas of image processing, or I should say in broadly convolution neural network, then you will feel more, if I talk about those things, then you will feel more motivated and connected with this ideas. But before I kind of jump into this concept, let me just try to set the context that the same idea which we have just discussed right now, we are going to kind of extend this idea in 2D, right? That's the first thing which I wanted to highlight, that it's nothing but we are doing a weighted average, and how this particular weighted average is going to help us. That's what we are going to discuss. But before that, when we talk about convolution neural network, apart from this weighted window, and nothing but this kind of observations, we usually talk about one particular term, which is called nothing but filter. So let me just, so as you can see, it's also coming over here, filter. So let me just try to give you insights what filters are, and then this particular convolution operator will make more sense, and then we'll go for some specific examples to make things more interesting and impactful. So the idea of filter, right? We have used this particular words multiple times in our lives so far. Like we talk about water filter. Nowadays we talk about air purifier filter. So what's the idea of filtering? So once you apply filter, let's say I'm applying water purifier filter, then what will happen? Filter will make sure that I get what I want. What I want absolutely pure water without any kind of germs or some kind of diseases, right? Or bacteria, right? Something like that. So similar to that, the idea of filter in the context of images will be once you apply that particular filter. For example, name of a particular filter is age detector. So from the name itself, it's clear that after I apply this kind of filter on the original image, which you can see over here, that it's nothing but sun's nice red ball, cricket ball, and a bat, right? Something like that. And now I'm applying this particular specific filter, which is called age detector. Then what I'm expecting? I'm expecting only the ages of this particular picture or boundaries of this particular picture so that I can identify objects properly. Now, how to get this? That's a different thing. I will come to it very soon. But hopefully the meaning of this particular word is clear. What's the idea of filter? Now, let's again try to shift to 2D from 1D with the similar idea of weighted average and how this particular window thing will work on two-dimensional data rather than one-dimensional data, and what will the impact of it, and how we can will be able to kind of establish this particular bridge, the idea of this weighted average with this kind of age detectors, and then things will be more clear. So let's just go through this particular second visualization which I have prepared. So as you can see here, in this particular case, as you can see, I have this kind of input. So usually our inputs will be of nothing but images. So either it can be a black and white image or it can be a colorful image. So depending upon that, we will have 2D or 3D structure with respect to this matrices. But with respect to this particular simpler example, I have taken hypothetical values between 0 to 255, which will correspond to nothing but pixel values. And let's say my image is very kind of, I should say, uh, low resolution. So therefore, I'm going to have only this particular matrix. As you can see, that if you just count it, so as you can see, it has 6 rows, and as you can see, 6 columns, right? So it's 6 cross 6 image we have. Now, how the idea of weighted average will work in this particular scenario. So let's just go through it before we talk about the technical aspects. So let me try to zoom this so that you can focus on the corresponding aspect of this particular visualization. So yeah, so hopefully, yeah, this much is, yeah. So this, yeah, but here it's okay. Means we can do this multiple times. So just focus on the window for now. That how the window is moving in this particular grid of 6 cross 6, and then we'll come to the what we are going to get in terms of outcome. So as you can see, the window is moving just like in the case of 1D, we are moving one step towards the right. So one column we are moving every time towards the right direction, and we are going like this, top to bottom, left to right, as you can see, right? So the box is moving like this. So if I try to zoom out, so you will be able to see that what is happening. And you can see every time we are going to give decision for nothing but center pixel, right? So now a couple of things we can observe, and kind of from the intuition we can kind of guess that why this kind of weighted average makes sense when we go for nothing but images. So let's just go for any kind of image. So let me just go to Google Images, and let's say image of India, or maybe let's say image of Taj Mahal, right? Something like this. So now, if we just look at into this particular image, right? So that there can be multiple questions which we can ask if we just observe this particular image. So, for example, if I consider this particular region of this particular, so hopefully my cursor is, yeah, it's visible. So if I focus on this particular green region of this particular image, that, let's say I'm going to do apply some kind of object detection or some kind of classification, some kind of task I'm going to apply towards the end with respect to this particular image. But do you agree that the outcome of this particular green point, which I have kind of highlighted right now, let me just try to zoom it so that you get what I'm trying to say. So consider on this particular kind of tiny, I should say, nothing but branch of tree. So whatever outcome I'm going to say, let's say I'm trying to classify whether this particular image has grass or not, whether it has trees or not, something like that, whether it has water or not. So do you agree that the decision of this will be mainly depending upon surrounding area, right? Do you agree that there won't be any trees in the nothing but cloud area of this particular image? Or if I look at towards the sky, then I won't be able to see water over there for sure. And if I'm looking towards the kind of downside of this particular image, then presence of water is also continuous. As you can see, if water is present over here, then surrounding pixels are also going to say water is there. Right? Usually that is the thing when we talk about images. Similarly, if I try to classify whether this particular image is of monument or not, then focus on the middle segment of this particular image. So not only kind of any isolated, I should say, pixel is contributing to this particular final decision, but surrounding pixels are contributing equally in some sense. So that means whatever idea of filtering I'm going to apply, that idea of filtering or that idea of kind of capturing weighted average must be focused on neighborhood of that particular image, right? So maybe the better kind of image will be image of Taj Mahal with pixel values, right? So then you will and division, something like that, grid division. So then you will be able to relate with what I'm trying to say. So what you can do now that if you look at into this particular image, so try to divide this particular image, as you can see, into nothing but pixels. So each pixel contributes to some information. And now if you see carefully, then the similar kind of pixels are appearing close together, right? So if something is absent, then those values are appearing together, even though this is not what we are going to apply, because the pixel things is entirely different. This is kind of art, but still you can see the whenever the image kind of black region is there in our original image, we can see series of tens in our outcome. So that means what I'm trying to say, if similar kind of structuring is there with respect to nothing but our images, then those structurings will be reflected in the corresponding pixels value, and this will help us with respect to decision making. And therefore we are going doing like this, that our
Sir,
kind of
but
window of weighted pixels. Yeah. Any queries?
sir, yes, sir. Sir, this would not be true when we are around the boundary regions.
Yeah,
This
of
is
course,
only
of
true
course.
when we are in the middle of it.
Of course, of course. I'm coming to do all those things, but for now, I'm just giving you the intuition. What is the use of nothing but filters, and why they are designed like this, right? Someone can ask when we go through this particular visualization, someone can ask why we are going for this kind of P cross 3 regular pixel filter. Why we are not kind of trying to get sense what is happening with respect to, let's say, corner 1 and corner 2 and combining it. Because it's very unlikely that those long range dependencies will have impact on our overall outcome. Of course, they will have some impact, and it will be eventually captured with the help of this filters. So give me some time, like after 10-15 minutes, these things will be clear very soon. But for now, let's just focus on that how and what kind of things are being captured by this filters. So as you can see, as we go along, we are going to get some kind of outcome. And first thing which you can notice is there is a mismatch with respect to your input and output feature map, I should say dimension. The input was 6 cross 6 and output is 4 cross 4. Can anyone guess why this is happening? Why we got reduction from 36 values to only 24 values? What we are lacking? So as you can see, we are in every iteration, we are giving decision for that particular middle pixel. So if we get decision for all the points, then our dimension will remain as it is. But as rightly pointed out by one of the participants, sorry, I couldn't hear your name, that the boundary points we are not considering, because I'm not giving decision for this particular pixel which is having value 42, right? So let me try to zoom this so that you can get what I'm trying to say. So I won't be able to place my filter where 42 will be at the center position, and this is true for entire first row, and this is also true for entire first column, and this is also true for the entire last row, and this is also true for entire last column. So now you can imagine it's very straightforward that from 6 cross 6 you need to remove 2 rows and you need to remove 2 columns, and then the dimension will be 4 cross 4, as we can see right now, right? So that's the relationship between this input field and feature map. Now the next question will come, why we are calling this feature map, what's so special about it, and what filter is trying to do. For that particular purpose, I have created this particular example so that the idea of filtering becomes crystal clear. So let's just go through this, and this will solve almost all of your doubts with respect to convolution. Why do we need it, and how it's going to help us with respect to a lot of things. So the first thing, as you can notice over here, is let's just focus on the values of this particular filter, which is nothing but age detector. And you know the purpose of age detector, because many of the times, just like Taj Mahal, that if I would just like to know whether this particular image is of a monument or not, even with edge detector, I will be able to say it, because most of the times I will be interested in the shape of this particular monument, not the other aspects, right? Color and all, right? Because if my task is just to classify whether this particular image is of a monument or not, then other things are not that much relevant. So now, if we just go back to this particular visualization, let me just go back to there, and then, okay, so let me just try to close the 811 things now. So yeah, so this is also fine. So let's just go back over here. So now let's just try to focus what we are going to do with respect to this three value, this 3 cross 3 filter. So let me just try to focus only there, and then we'll discuss more. So as you can see, the values are -1, -1, -1. All values are -1, except for the middle value, which is nothing but 8. So what we are going to do over here, what we are doing essentially over here is the decision making pixel for which we are making decision. We are saying that increase your value by 8 times. Your pixel value you need to increase by 8 times. And for the surrounding pixels, we are saying that you need to decrease your value by -1. So we are just ignoring them. Right? So basically, so let me just try to explain you with this particular example of, let's say, if we again go back to the image of Taj Mahal, then this will make more sense. So if I just go to this, let's say over here. So now imagine a scenario. What will happen to this if I apply this particular filter on this particular sky region? All the pixel values are more or less same. Do you agree? Then what will be the impact of this particular filter, weighted average? Again, let's just read the values. So imagine that all the pixel values are towards 200, and I'm applying this particular filter. What will happen? Can you count how many -1s we have? Exactly 8. So what I am doing, I am multiplying the middle pixel with, let's assume its value is 8. x, and what I'm doing, I am multiplying its value by 8. So what will happen? I'm saying your value is 8x now, but you need to subtract whatever your surrounding values are. Right? One time you need to do this. And for how many neighbors you need to do this? Exactly 8 neighbors. Now, what will happen if all the surrounding neighbors are also having the same value, which is nothing but 8, x? Then what is happening essentially, that in the if you focus on this particular image, then you will be able to relate with it. What I'm trying to say, consider this particular sky region where we can see a lot of symmetry with respect to at least out visually we can see that it's very much consistent image. And now what will happen over here, that I am saying that middle pixel increase your value by 8. So what will happen by factor of 8? Its value will become 8x. And since all the surrounding pixels are having same value, which is nothing but ax, I am decreasing, I am subtracting x 8 times. So basically what will happen? 8x minus 8x, which is essentially become nothing but 0. And therefore we will be able to see black, right? So that's what happening over here. If you focus over here, why these things are looking nothing but exactly black. If you notice over here, then this entire thing was consistent with respect to green color, all right, or some other color like red or red, whatever other color like white. For all those things, what is happening? Since surrounding pixels are having same value, what is happening? Essentially, what we are doing. Let's assume that all the pixel values are very close to, let's say, x, and then what I'm doing, I am multiplying the middle pixel with 8, and then I'm subtracting exactly 8 times x. So then what will happen? 8x minus x 8 times, then I will get 0, which is nothing but blank. And something strange will happen with respect to boundary points. Now you can guess what will happen. With respect to boundary points, these points will survive, because what will happen with respect to this edges, if you focus on this edges, we can see some variety over here. With respect to edges of this particular structure, the above this particular kind of semicircular shape, we can see cloud, right, or sky, and therefore the color is different. And below that particular circular region, semicircular region, we can see the monument actually, and the pixel values will differ. So basically, there we are going to get only at those regions we are going to get different values, non-zero values, and except for that, all other places we are going to get zero values, and that's how this particular filter works. Similar to this, so hopefully this idea is clear that what is happening with respect to this. Similarly, if you give kind of same value to each and every pixel, that same weight to each and every pixel in neighborhood, then we are going to blur the image. Similarly, this kind of filter can be utilized for sharpening the image, right? So when we go for this kind of tools like Adobe and all, so under the hood, they are applying this kind of filters only so that we get different variations. Or even if we check with respect to our kind of nothing but apps which we are using in our cell phone, there also this kind of things are happening in under the hood, where basically it's this convolution operator, as you can see, and it will run through the entire kind of image, and we will get the modified image as per our filter choice. So hopefully the idea of filter is clear now. Now the next important thing is why it is called feature map. So now things will become more interesting. So why we are applying this filters, right? From hopefully from the yesterday session, the objective is clear. We would like to do some kind of task. Let's go for the simplest possible task which we can think for. Usually it's called hello world of deep learning or machine learning, when we talk about nothing but this MNIST data set. So in MNIST data set, what we need to do, we need to identify what handwritten images are given to us. And then basically we need to identify what is the image corresponding to, right? So let me just go to some example of it, then it will become more clear what I'm trying to say. So in input, we are going to have, yeah. So in input, you can see we are going to have this kind of images, but the same numbers can be written very differently. As you can see over here, zero, if humans are writing this particular numbers, then they can write with varieties of options, right? These things are not digital. These images are human written. And so from the name itself, it's clear that what we are trying to do, handwritten digits are there, and we would like to recognize that handwritten digits with the help of some kind of neural network, whether it's artificial neural network or convolution neural network, doesn't matter. But we need to learn some kind of patterns. And we are talking about patterns because this is relevant to nothing but our filters. So each filter will try to grab some pattern, whether that particular pattern is present in my image or not. For example, when I talk about 9, then usually irrespective of how the person is going to write 9, there will be some circular shape which will appear in my image for sure. So I can have one filter which will try to capture those kind of circular kind of nothing but shapes in my across my image or not. So if I give you very simplistic example, then consider the case that you have some kind of chain, keychain. Let's say, let me just try to show you. Let's say this is the shape of that particular keychain, right? And you have somehow lost that particular keychain at your home, and you know that it's there in one of the rooms, but you don't know where it is exactly, right? So then what you will do? Let's say it's corresponding to your drawing room. So what you will do? You know that your keychain is in that particular room. So in your mind, you remember that how your keychain looks like. And what you will do, you will divide your room into small sub segments. You will start from, let's say, very first row of your nothing but room. So imagine now this is your room, and you are trying to search for that particular nothing but keychain. And this particular filter is nothing but image of that particular keychain in your mind, and also its size. So that granular nature also makes sense because the keychain size is very less. So therefore, my filter size will be less accordingly, because I will try to look for that particular keychain across my room, and I will start from the different segment. Let's say I will first kind of consider the segment which has sofa in my room. And then once, let's say, first two rows contain sofa, then once it's finished, I go for the next row, like that. And I will, if I kind of religiously kind of scan this entire room, and if my kitchen is certainly there in this particular room, then I am going to find it for sure, because I'm scanning this entire room from left to right, top to bottom. Same thing we are doing with respect to convolution operator in 2D. We are doing this particular process throughout the image with respect to multiple kind of filters, because we would like to identify. So filters are nothing but they are helping us with respect to identifying different patterns. So what I would like to do is I would like to find out different patterns across the kind of images. And for one particular image also, I would like to find out series of patterns, so that therefore I can have multiple filters. And whatever these particular filters are giving us, we are going to store it in one particular format. Why that particular format is called feature map? Because basically it's giving us some insights about the image. And whenever we talk about something insightful in the language of machine learning or deep learning, we say it's nothing but features. Because in some sense, if my filter is corresponding to nothing but identification of nothing but circular pattern, then the one value in that particular feature map will say that yes, that particular pattern is present in your image, and zero value is corresponding to nothing but that no, that particular pattern is missing in your nothing but original image, right? So maybe I can briefly showcase you this over here. So as you can see, if I talk about this kind of number like 2 with respect to MNIST, then you can see the differences with respect to white pixel and black pixels. Whenever that particular number is present, we can see values are closer to 255, and whenever the number is kind of digit is missing, we can see values are very close to nothing but zero. So I will come to this afterwards, but let's focus on this particular filter which I was mentioning, that when we talk about this kind of circular pattern thing, then basically we are going to scan this entire image from left to right, top to bottom. And this is the beauty of convolution neural network. Of course, I will not talk about convolution neural network yet, but the convolution operator itself, that irrespective of, it's called location invariant feature, that irrespective of where this particular circular pattern is, eventually we are going to find it out, because we are scanning this entire thing. That's the core idea about this convolution operator. Right. So as you can see, we are going to get this kind of feature map towards the end. Of course, I will come to this formally, that what are the issues with ANN and why do we need CNN. But for now, my focus is on this convolution operator, so that you can understand and appreciate what we are doing. So as you can see, let's say if this is my filter, and if I exactly the same pattern, it's like a keychain matching, as you can see. So let's say my keychain is over here, and the moment I put this particular kind of my virtual eyes, which has this kind of detector, let's say keychain detector, then it will signal that yes, 100% it's nothing but your keychain. So the same thing we can observe over here. So whenever the window we are sliding towards that particular exact location where that particular pattern is there, we are going to get one in our feature map for sure. And that's the idea of this filter, that its sole responsibility or job is to identify this kind of tiny patterns initially. And of course, we'll see later on that how those tiny feature map will help us with respect to identification of high level features also in long run, right? So as you can see, if we are going for this kind of loop detector, then it can be reused multiple times. It will be useful for 6 also. It can be useful for identification of 9 also, right? So, and the location variant thing I've already kind of highlighted. And the core idea, as you can see, for the same image, we can have multiple filters, and therefore we can have series of feature maps, which is going to help us with respect to our classification task. Okay, so now this much is sufficient with respect to kind of nothing. But of course, there are some other aspects about size, but I will come to it in a while. Let me just try to focus on practical aspects first, and then we'll talk about the remaining important aspects about nothing but I should say filter size and how it will impact with respect to nothing but our size of feature maps. But let me just go through this particular visualization in order to give you some ideas about some of the important things, and then we'll talk about convolution neural network thoroughly, and then I will showcase you two different data sets on which we are going to apply nothing but practically convolution neural networks, and how it offers us better solutions or better results with respect to nothing but classification problems with respect to in the comparison to, I should say, artificial neural network. So let me just try to focus on some important insights with respect to couple of, I should say, hyperparameters, setups, and fundamental knowledge aspects of convolution neural network. So first, I'm going to talk about what's the relationship between nothing but filter size and output size, right? Let's say I'm starting with 6 cross 6. Why I'm getting 4 cross 4 output while I apply this 3 cross 3 filter, and what's the generic formula for it? So in general, let's say if user is giving us nothing but let's say if we are applying filter of, let's say, k cross k on image size of n cross n, then what will be the output size? And why we are referring to this output size, why the calculation of output size matters, it will become evident very soon, because it's connected with number of parameters or number of and number of parameters. Again, it will decide the complexity of the model, that how much training time will be required to train this particular model efficiently. So therefore, it's important to know that how these things are related, and also some other concepts which are very much aligned with the nothing but concepts of convolution neural network. So let's start with the first idea, that how this impact, what will be the impact of this filter size on output? That's the question. It's very straightforward. So we have already observed this, that once we go through this particular process of going from left to right and top to bottom, as we do like this, we get these values. But why we are getting only this 16 values? Why we are not getting this 36 values? That is the question. So as you have noticed earlier, that for every pixel, in some way, we are giving decision for this particular middle pixel. And if you notice carefully, then as we slide this window, there are some candidate, I should say, pixels, which will never be in the center. For example, this first row, it cannot be in center. This left row, leftmost row, it cannot be in the center. Rightmost row, it cannot be in the center. Similarly, this, I should say, column, leftmost column and rightmost column, they won't be ever in the center of this filter. Similarly, the last row, it won't be ever in the center of the filter. So therefore, what will happen? We need to reduce this 2 rows and 2 columns from our outcome. So therefore, the number which we got is nothing but 4 cross 4. But this is not true in general. For example, if you notice carefully, then what will happen with respect to 5 cross 5? The entire different thing is happening if I increase the filter size. For example, over here, if I kind of you can imagine that even though this particular it's not working over here with respect to 5 cross 5, I will make sure after some update it works. But you can imagine that what is happening with respect to 5 cross 5. I won't be able to get series of I should say rows and columns in my as my center of filter, and therefore I there will be a significant reduction in the size of output. As you can see, initial size is 36 pixels we are having, and output size you can see only 4. Why this is happening? Can anyone guess? Because if you notice, then I can shift this 5 cross 5 filter just once with respect to right hand side, and then I can apply this just 4 times. That's the reason. If I cannot apply it more than 4 times with respect to this setup. So in general, what is the formula which we can apply in order to get sense of output? That formula is written over here. You can see it's nothing but what you need to do. Initial size is 6. You need to subtract whatever the filter size is, which is nothing but 5 cross 5, and add 1. That will be the output size. And this all these matrices are nothing but square matrices, so therefore it's easier to understand what is happening. So if we see 2 cross 2, then what will happen? 6 minus 2 plus 1, which is nothing but 5, and we can verify we are getting 5 cross 5 only, right? So I'm not going into the details of this, but this is just for your knowledge that is how it works. Let me just go to the one more important aspect, which is called striding. What's the idea of striding? Striding means how we are shifting our nothing but so in day-to-day life, if we are using any kind of fitness apps, then maybe you have heard this word, which is called nothing but stride. So it's corresponding to step. So not necessarily our window, our 2D window of filter overlaps. For example, over here, as you can see, currently I'm focusing on this first 4 pixels, and in the next go, I'm focusing on the next 4 pixels. So here stride is, as you can see, 2, not 1. So now there will be a significant reduction in the number of pixels which will be in the center of this nothing but I should say my filter, and therefore roughly as you can see I am skipping every second pixel. So for example, over here, if I do this traditionally, then my my next window will capture 8316, but it's missing. So therefore I have missed one particular opportunity, and this opportunity will be missed for every window which I am considering, right? So therefore, whatever I am getting earlier, I need to divide that particular thing by a factor of 2. So therefore, you can see this particular factor of 2 is appearing for slide 2. If my slide is 3, then that factor will be 3. So it depends upon my stride or step value, that that much reduction will be there in my output size. This is just for your knowledge. You don't need to remember this. Or anyway, I have shared this particular visualization with you, so you can go through it again in order to get better sense of it. But this much understanding is sufficient for us that what is stride and how drastically the output window size decreases as I increase my stride value. That much is sufficient. For example, if I take stride value is equal to 3, then you will be able to see that even though it's not working right now, yeah. So now if I drag it, then you will be able to see that what will happen when I go to the second iteration. I'm skipping this entire thing, right? 3, 6 won't be ever considered in my final outcome, right? So that's the impact of stride. The next important thing is like, again, if we go back to the only question which we have received so far, what about the boundary points? So this is the solution for boundary points. So since boundary points were not appearing in the center in any of the iterations, how we can include them with respect to some kind of decision making or capturing the features, the answer for it is nothing but padding. Add a border row as well as column before the start of the actual image, and this border will contain nothing but 0 values, right? It's nothing but kind of, I should say, black border, right? 0 is corresponding to black, right? So we have just added black border across our image in order to ensure that now we get some representation from this particular boundary pixels also, right? So that's the idea of this nothing but padding. Okay. And again, one more important thing about nothing but this convolution operator before we go directly towards nothing but framework of convolution neural network, and then nothing but actual implementation of it. I would like to highlight just two important things. The first one is, even though your input is 3D, the sliding is done with respect to 2D only, because for each filters we are going to assume that the depth of the filter is same as depth of nothing but my input. So therefore, even though we are doing this with respect to 3D images, we are with respect to nothing but filtering process, you can assume it's 2D only because of this setup, right? So every time filter depth is nothing but depth of your input. You just need to remember this. That's it. Next important and aspect without which convolution neural networks cannot work is idea of pooling. What's the idea of pooling? Let's just go back to this feature map. We have got a lot of features which are present over here. But as you can see, if I try to zoom this, then it will make more sense. Some of the values don't make sense at all. Right? For example, is it good to say that something is minus 0.11 times present, right? Minus 11% chances are there that this pattern is present in your image. It's very bad way of saying it. So I would rather say it's 0%, right? So that is one limitation. And from the yesterday's discussion, maybe it's clear that how we can rectify it. There is one beautiful function which will help us with respect to eliminating this kind of negative numbers. It's called a ReLU function. What's the idea of ReLU? If something is negative, then make it 0. And if something is positive, then keep it as it is. Right? It's very simple. I'm repeating one more time. If something is negative, something means I'm referring to numerical values. If numerical values are negative, then make those values 0. And if numerical values are positive, then keep them as it is. Because we are talking about presence or absence of nothing but features in some on some numerical grounds, and negative values don't help us with respect to that particular task at all. So therefore, we are just going to eliminate them with the help of one interesting function which is called nothing but ReLU. So as you can see, ReLU, what is the idea of ReLU? This is the um, uh, kind of plot of it. As you can see, it's kind of y is equal to x line with respect to first quadrant, and all other places it's going to be 0, as you can see. So if I give this input to my ReLU function, then what it will do, it will just keep all the values 0 apart from positive values, and positive values will survive only. That's the idea of this cool ReLU function. Now, next important thing is that with respect to a particular filter, we won't be interested in some low magnitude values. Why? Because they are not going to contribute anything. So let's say I am trying to identify this kind of circular patterns, and at some places I am getting higher values like let's say 9, 8, and in some places I am getting very low values like 0 or 1. And as you know that ReLU won't kill this 0, 1 kind of values because they are positive. So now what I need to do, if I keep this input as it is, then it will take a lot of resources of mine. And apart from that, it's not contributing anything. So for example, if I say that something is probable with 9x possibility versus if I'm saying that something is probable with x probability, then towards the end, I would like to focus on only the places of my images where 9x kind of promising 9x numerical value representation promise was given to me, that 9x times it's likely that this particular kind of pattern is present in my image as compared to x time presence, right? So of course, so basically if my example is corresponding to these two values, 9 and 1. So this 9 says that if I'm assuming that this 1 is corresponding to, let's say, x, 1 unit is corresponding to x, then this is saying that 9 times more likelihood is associated with this set of pixels rather than this set of pixels. So what I need to do, I need to ignore this 1 for sure because it's not contributing anything with respect to my final outcome. But I cannot do this randomly because again I need to take care of that neighborhood thing, because many of the times, let's say at distant neighborhood, distant location of the image, some less values may also contribute to some kind of feature presence. So what I can do, I can just do this locally, that in my neighborhood, who is the winner? I will just take that particular value in my final outcome. I won't consider other values. This idea is called nothing but pooling. That instead of considering this four different values, let's say I'm applying pooling with window size 2 cross 2, then what I will do, I will consider the four local hood pixels, and if my pooling strategy is max pooling, then I will pick the maximum value out of those four. And let's say 8 is there with respect to this four. So only 8 will survive. 5, 1, 2 will be killed because only the dominant pixel value offers us promising yes with respect to feature presence. That's the core idea of pooling. And apart from it, the rest of the things like rolling out this particular max pooling window with respect to our image from left to right, top to bottom is consistent with our idea of nothing but, I should say, filter, right? So if I go back to my visualization, then it will become clear that what I'm trying to convey. So as you can see over here, if I just go over go to this next step, then you can see why 10 is appearing here over here because 0, 3, 6, 10. So the winner is 10, of course. So therefore, we are going to have 10 only. That's it. So that's the idea of this nothing but pooling earlier. And as you can see over here, shrink each feature map without kind of weights. Why this is important? Here, some students confuse over here that we need to have some kind of more parameters while we do this. But this is nothing but we are just applying one simple Python function which will just reduce the size of our feature map. That's it. Nothing else. So no weight training or parameters are involved in this particular crucial step. So now, I guess in the first roughly 1 hour, I have set the context thoroughly, and we are ready to learn about convolution neural network formally. And first, I will demonstrate the overall architecture of convolution neural network, combining all these pieces, how they combine, and why that particular combination makes sense, and why that combination eventually offers us for the series of data sets significantly better results as compared to traditional ANN, and that will the flow for the rest of the 1 hour. So now I will just consider one more presentation which I have prepared, right? So we can ignore this because I have read a couple of your kind of chat messages where you have suggested that only the multi-layer perceptron has been covered properly. So I will skip that particular part and let me just go to yeah, just a second. Let me just go to uh, this presentation of mine so that we can put everything together, whatever we have discussed so far. We'll quickly revisit this, and then straight away we'll talk about MNIST and how we can get better results with respect to that particular digit classification task. So the problem which we are going to address is handwritten digits are there, and we would like to identify what that particular digit is, which digit is written with the help of our convolution neural network model, and that too with very high accuracy. That's the objective, right? So yeah, any questions up to this point, or maybe I will just first cover some ideas of the core ideas of CNN, I should say thoroughly, and then I will check the uh, kind of just a second. Okay. Okay, fine. Yeah, couple of things are there, but I will come to it very soon. So Sandeep ji has asked a very nice question. It's about is CNN heavy because it scan whole image? Very good question. I will reply to this question very soon, Sandeep ji. Yeah. So the first thing which I should kind of focus on is that as you can see, flattening makes nearby pixels look unrelated. That's it. Flattening means what's the idea of flattening? And why flattening is required? That is the first question I should address before we go ahead. So let me just try to, okay, just a second. Let me just try to share my screen one more time because there was some error with respect to movement of cursor. Uh, Fine, but hopefully it's, oh yeah, now it's fine. So let me just go to this why flattening is required. Let me just try to explain that so that you will appreciate this very soon, even though It seems that we are spending too much time on theory, but after 15 minutes, once I start practical kind of demonstration with respect to this Colab notebooks, which I have prepared beforehand, you will be able to appreciate all this and everything will follow very smoothly because we have spent significant time to this fundamental aspects. So what I'm trying to focus over here is that why flattening is required. Let's try to understand it. So the first thing is what is the size of this handwritten images in with respect to MNIST data set? It's 28 cross 28. So we are going to have 784 different pixels. That is the first thing. And now in the initial, right from the yesterday's discussion, it will be clear that each neuron of the initial layer of neural network is capable of kind of accepting only one pixel value, right? So that's the limitation. So therefore, what we need to do, if we are having this kind of pixel values, we need to convert it into some kind of 1D array, which we can later on feed to our neural network. This process of converting 2D matrix into 1D array is called nothing but flattening. So as you can see, it's nothing but we are just copy pasting these pixels row by row from top to bottom. That's it. That is the idea of flattening. Okay. But while we do so, we need to kind of ensure there is the issue while we do so. All right. What's that particular issue is that is listed over here, right? So if we go back to my slides, then you will be able to appreciate what is the issue. When we do so, we are missing out on the something very much important, which is called nearby pixels, because they will be far apart in our long vector now, right? So that's the issue while we do so. Okay, and therefore we now it's clear why we need convolution, because most of our decision making is based on local context, and therefore we can't. Of course, the global context will also come, but this local context will help us not only to capture local context, but in long run global context also. It will become very clear when I explain the entire architecture. But for now, why this idea of, so from this discussion itself, it's very much clear that the first step of our implementation won't be flattening for sure, which was true for ANN. If you would like to implement the same thing in ANN, you need to go for that flattening thing straight away and feed the pixels to neural network and will start working. But with respect to CNN, we need to do something else, which we have already discussed, which is nothing but idea of convolution. So we have already discussed this idea of convolution with respect to this nice cricket example. So hopefully it's clear what is convolution. So we are going to kind of go through left to right with respect to 1D convolution. But so basically, remember, we are going to multiply this weights. And why I'm calling this weights? Because eventually this is going to be learned by our neural network. For now, I am explicitly saying that give 50% importance to this middle reading. But in general, when we talk about the actual problem, this weights will be kind of learned by our model by itself, right? So that it's a trainable parameters, right? I should say. And finally, based on this multiplication, we are going to give the revised estimation of the actual speed. Okay, so basically slide, multiply, add, and record in our feature map. These steps we are going to repeat when we talk about convolution optimal. Sliding means the window is moving from left to right. Multiplying means we are going to multiply the corresponding pixel value with the weight values. Then we are going to add those values and give the final decision. And we are going to store that particular final decision in our feature map. That's the idea. So in the 1D scenario, we say it's a smooth signal. With respect to 2D filter, with respect to images, we are going to say it's nothing but feature map, right? And as you can see, this is the corresponding equation. It looks slightly complicated, but the core idea is which I have conveyed to you already. So as you can see, this is how we are going to move left to right, top to bottom, and corresponding feature map will be filled for sure. Okay, so now let me talk about the entire architecture of CNN now. Before that, why ANN fails and what are the limitations of ANN, so that you get the full picture, and then straight away we'll jump to the implementation part. And I will also share the corresponding Colab notebook so that you can recreate these implementations and you can relate with this particular topic very smoothly. So the first limitation of, I should say, ANN will become evident when we consider colorful images. So consider any image which you have captured with the help of your cell phone. It will have this kind of dimension: 1920 cross 1080 cross 3. Why this 3? Because I am referring to colorful images. Nowadays, that it's hard to find a cell phone which captures black and white images. Of course, we can have a filter which can convert an image into a black and white image, but by default, it's a colorful image. So now, if you just count how many pixels are associated with this image, then it's roughly 6 million, right? And if you are just going to use only one layer, one hidden layer, multi-layer perceptron, with first layer just there to capture the input, and last layer is just to kind of give us the output, then also how many parameters will be required? It's a huge number. Let's just try to understand it. That 6 million neurons will be required just to get data, just to get input. Just like in this particular case, 784 neurons will be required just to get input of this 28 cross 28 grid. If my image is colorful, then that numbers goes to this 6 million. 6 million is a huge number. And usually when we create any artificial neural network, we must have some kind of hidden layer also. So let's assume that we have just one hidden layer with 4 million neurons in it. And then if we just try to understand how many different weights will be communicating, then the number will be huge, like it's a 24 million. It's a very huge number, and it's very much difficult for our artificial neural network to train over this massive amount of weights, right? So therefore, for colorful images, our ANN system will fail miserably, right? So that's the first disadvantage of ANN, right? So as you can see, 24 million parameter, it's a huge number, and therefore it requires too much computation, and we can't go ahead with it. Second issue is its location invariant feature is missing. So that means it's going to treat local pixel as similar to nothing but pixels which are far apart, mainly because of that particular flattening thing. It's not focusing on location invariant aspect, right? So so that means what I'm trying to suggest over here is, if my model will work well if every time 9 is present nicely like this at the center of the image in my all training data sets, right? But if 9 is shifted somewhere else, then my model will fail. I'm talking in the context of artificial neural network. So that is one more disadvantage, which is that it is not location invariant, right? So that's there. And so that is again corresponding to nothing but eventually it's sensitive to location of an object in an image, like I mentioned, that I must have some consistent kind of data, then only it's going to perform well with respect to outcome, and with respect to MNIST, it's going to perform decently because all the images are centrally aligned. But in general, it won't be true. And also, MNIST dataset is nothing but, I should say, black and white images. It contains black and white images, but in general, we can have this kind of data where images are colorful, where there is no way we can go for ANN for this kind of data, and therefore we need some different measure, some different technology which can essentially do the same task but with significantly less computation and more intelligence, and that's what CNN does. So before I talk about CNN architecture, let me just walk you through with this particular first iteration of this particular model, which is nothing but our artificial neural network model, where we are going to apply the yeah. So as you can see over here, there is no CNN involved, and let's just understand what this particular basic model has to offer, and then we'll talk about CNN and how the results will improve. Meanwhile, I will straight away, yeah, I will also talk about overfitting, but let me just talk about the foundational aspect, because I don't want to deviate too much from the core ideas of CNN first. So let me try to cover the CNN in decent detail, and then if overfitting is not covered yesterday, then I will cover it also, right? So I'm not sure whether it was discussed yesterday or not. So therefore, I just skipped that particular piece of information, but soon I will come back to it if required. But meanwhile, let me just try to create a copy of this. I'm running this on Google Colab platform, and hopefully all of you know what Google Colab does. But even if you don't know, it's very simple. You can just straight away go to this Colab. You can just search Google Colab right on Google, and you just need to upload the file which I'm going to give you, and then you will be able to run this for sure. So let me just try to share this particular file with you so that you can get the same experience. So anyone with the link, I am providing the access of uh, that editor, but make sure you don't modify in the same copy, otherwise the other people will struggle. So create a copy of whatever I'm giving you and go for that. Uh, you can just run this to get sense of it. But what I would like to do now is let me just try to share this with you so that you get the idea of what we are going to do properly. Okay. So yeah. So yeah, I will come back to your questions very soon. But for now, let me just focus on the foundational aspects, and most of the questions will be answered while I present this. So the first thing which we need to do is we need to install this standard libraries, TensorFlow, Matplotlib for visualization, numerical computations, NumPy. The main work starts from over here. So just like our semester exams, right? What we will do in our semesters, we teach very nicely. We give a lot of assignments, but the main part which matters with respect to students is nothing but our final end term examinations, right? That is nothing but test. So just like that, and also we can have a series of kind of examinations during the classroom also. Classroom based on classroom activities also we tend to give some kind of scores. But usually those scores won't reflect much on the final CGPA or final grade which we are going to provide. Final grades significantly depend upon how well the students are performing on the test data or the test question papers, or how nicely they have scored in the midterm as well as end term tests, right? And based on that only we'll say how good or bad the student is with respect to knowledge of that particular subject. Similar to that, in deep learning, we are going to split our data. So imagine that you have prepared 100 questions, right, with respect to your whatever subject you are teaching. Let's say you are teaching generative AI to your students, and you have created around 100 important questions. Out of 100 questions, 80 questions, or let's say 70 questions, you are going to discuss in the class. You will also provide solution of those 70 questions in the class itself. And how likely that you are going to ask the same 70 questions during the examination? It's very unlikely, because you know that all your students already know the questions, they already know the answers, and if you ask the same questions in the end of examination, it's very likely that they will answer without any struggle, and it won't evaluate their reasoning capabilities or their skills, all right, and their application skills with respect to the subject. So what you will do, out of those 100, the 30 questions which you have kept aside in the beginning, you will judge your students based on those 30 questions, and you are going to definitely ask those 30 questions in the midterm or end term examination. That's what we do usually. And same things apply with respect to this deep learning model. So as you can see, I am going to divide my data. I have 70,000 images, but I will keep 60,000 images for training and 10,000 images for testing. And how well my model is going to perform with respect to this test data, that will decide the kind of capabilities of my model. So if my model is working well with respect to test data, its accuracy is good with respect to test data, then my model is good. So that's the context of testing and training. And during the training period, we won't show the test data. Similar to while we teach, we won't disclose our end term question paper in our classroom. Similar to that thing is being set up over here, as you can see. And over here, you can see, imagine that all your 100 questions are MCQ questions. Then with respect to kind of giving marks to your students, you must know what are the correct answers with respect to those MCQs. So the questions have been stored in X, and corresponding answers have been stored in Y, right? So as you can see, these things are coming in pair: X test, Y test, X train, Y train. So for training also we know the answers, for testing also we know the answers, because this is supervised learning setup. Okay. Now the next thing is very simple. We are dividing each pixel value by 255. Why we are doing this? Just for normalization, so that every values come between 0 to 1. We want this that particular consistency, and usually machine learning model works well when they come from this kind of limited range like 0 to 1. And now if I just look at into the very first image, then it will look like series of 784 values with some pixel values 0, some values non-zero, depending upon what it is there. If I try to see the shape of this image, then as you can see, it's 28 across 28. If I plot it, then you will be able to see the actual image, as you can see, 5. So now what should be our goal? I would like to have create some kind of nice model, artificial neural network model, which can automatically detect, given this input, it should be able to tell us this is nothing but 5, right? That's what we want. Without even human intervention, it should be able to do it. That's the objective. So now how to accomplish this objective? Similar to this, you can see we can plot any of the images from our training set and see what it's there. If I see the answer key, then in answer key, we can see these numbers 504. So let's verify. What's the answer of the first question? 5. Let's just see. What was the first question? 5. Right? So it's correct. This is handwritten 5, and my answer is also 5, which is consistent. Then second image in my training is corresponding to image 4. As we can see, it's handwritten 4, and my answer is saying it's also 4, right? So it's correct. Now the next thing is what we are doing. As I guess someone is trying to say something, I request you to keep your mic in mute mode. If you want to ask something, then go ahead. But otherwise, I request you to do so. Then the next thing which we need to do is, as you know, this is ANN, not CNN. So therefore, we need to flatten our input so that we can provide this particular input to our neural network. Because ultimately, I would like to solve this particular problem with the help of neural network, not with the help of humans. So what, and there can be multiple applications, like let's say pin codes usually written by humans, and we would like to automate that particular part that identify the pin code written, or maybe amount which is written in the check. I would like to automate. I would like to have one deep learning model which can give me directly what's written over there in the checkbook. Okay. So what I will do, since I would like to provide this particular piece of information, which is nothing but my image pixels, to my neural network, I need to apply this flattening thing so that eventually I can prepare my model and provide this particular data to that particular model. So therefore, as you can see, I'm going to reshape. I'm changing the shape of my input, and the changed input will look flattened. So as you can see, for all the data points, all the 60,000 images, I'm going to convert it into 784 cross 1. So that is happening over here. And same thing I am repeating for my test data also, because otherwise I won't be able to provide my data, whether it's test or train, to my neural network. That is it. Now the fun part starts, where we are going to actually create the structure of the nothing but our model, which is nothing but in this particular case artificial neural network, and then we are going to provide the actual data to it, right? So for creation, this part is creation, the segment which I have already kind of highlighted. This is the model creation, and data will be provided with the help of fit function, as you can see, right? So this is the second part where we are going to provide the data. Now let's just try to understand the component of this model creation part. So as you can see, the first thing which we need to understand is that there are 784 different values. So my input structure of my artificial neural network, input layer of my artificial neural network must have 784 pixels. So 784 neurons, I should say, to capture the pixel values of all those 784 pixels. So as you can see, input shape is 784 over here. And in my simplest setup, I don't have any hidden layer. I directly would like to give the output. So since my handwritten digit, if I again go back to that MNIST image, right? If I just go to MNIST data set, right? Then you will be able to see that only images are considered which are going from 0 to 9. So I have 10 different classes corresponding to each column of this set of images. So therefore, in the output, I must have 10 number of neurons. And that is what written over here, as you can see. So if you go over here, then 10. This dense means we are going to apply all the kind of neurons of first layer have been connected to all the neurons of the last layer, and we have only 2 layers for now. Activation function already covered, sigmoid. The optimizer, what is the role of optimizer? It will again help us to reach to the weight combination, which will minimize the nothing but loss. Which kind of loss we are considering? Sparse categorical cross entropy, that's the loss. There are some other losses also. We can go to them if time permits, but for now I'm just mentioning it. And then the metric is accuracy. So once this is done, then I have provided my Colab notebook, the structure of my model, but I haven't provided the actual data. So now I'm providing the actual data, that this is my data, this is the answers, and try to learn from these answers and repeat this for 15 iterations. So after every iteration, you can see The model is becoming smart. It's like I have written one nice book about my subject, and I am telling my students to read this particular book 15 times. So after every iteration, their knowledge will increase. Something similar is happening over here. As you can see, accuracy is increasing 87 to 91, 91 to 92, right? 93, 93, right? So after 15 iteration, you can see accuracy is increasing in every layer, every iteration, and loss is decreasing. So we are reaching towards the minima, which is nothing but zero. So we started with 0.47 and we ended with 0.24, right? You can run for, and again, this is hyperparameter, epoch. You can change it to 150 also if your time and machine permits. But for now, I just stick to 15 only. So model has been trained now. So now it understood that what it needs to do in order to identify the handwritten images. And out of 100, 93 times it's doing good work. But this, or it's giving the correct answer. But this number doesn't make any sense to me or doesn't contribute anything to me because this is training accuracy. Because I already disclosed the answers, and from answers it's learning. So therefore, it's not worth it. I am mainly interested in how well my data is or my model is performing on unseen data. What's the meaning of this particular word unseen? Unseen means it's not being seen by the model during the training. And that data I've already kept aside. If you remember initially, just like our question paper, we have kept this 10,000 images separately just to test how good our model is performing on unseen data. And if we just check that particular accuracy, then it will be the kind of the result for this particular model, we can say. So you can see now I'm just evaluating my model on this particular test data set, and you can see the accuracy is 92.69, which is good but not best. So it's like roughly out of 100, 7 times my model is performing wrongly. It's giving different answers, which is not appreciated, I can say. Right? In real world, this like someone to someone, let's say I would like to pay 15,000 rupees, but the model failed, and instead of one, it wrote zero, and now I'm paying just 5,000 rupees, right? So it won't make sense. We can't deploy this because the accuracy is good, but it's not good enough for sure. And let's just see what this model does. So let's just try to find out the outcome. So I'm just storing the outcome in one vector. So we are getting this kind of very huge vector of length 10. The length will be 10, I should say 10,000 entries will be there, and each entry will consist of one big vector of length 10. That's how it is. So now, so accuracy is very simple, Dr. Jayanti. Basically, we already know the correct answer, right? So we are not providing that particular answer to model right now. But if you notice carefully, then initially we have split our data into the kind of question and answer. So we know, like it's just like how we are giving marks to our student. Let's say 10 MCQs you have prepared, and you know the correct answers of 10 MCQs. Let's say I'm your student and I'm appearing for that particular examination, and I have given my answer sheet to you, and now you are evaluating, and you just count that out of 10, I have answered 6 correctly. So then you will say your accuracy as a student is 60%. That's what we are doing over here. But it's happening in the background. The Python functions are working in the background, which we there's an abstraction, right? This is kind of user friendly, so we won't be able to see those functions on the surface level, but in the background the same thing is happening, right? So that's how the accuracy is being calculated. So as you can see, we have 10,000 images, and for every image we are going to get this 10 length of vector. And now, so for example, if I just plot the first prediction, then it will look like this. We won't be able to understand anything out of it. That what it's trying to say. It's a series of 10 numbers, but they are very random numbers, and it's 10 raised to power -9 or whatever, right? It's difficult to understand what it's trying to say. So there is one more function which will help us from NumPy, which is called argmax. What argmax will do, it will just try to find out index of the nothing but this particular array where the value is maximum. So what it's saying, on location 7, the value is maximum. So that means for the very first prediction, my model is saying that it's very likely that your original digit is handwritten 7. And now I can check that what is the original image. Yes, it actually is 7. So makes sense. You can see. So now you will be able to understand everything, that this 10 is nothing but outcome of nothing but my artificial neural network for one particular image. Which image? This image. What it is saying? This 10 numbers it's giving. And I would like to find out, it's nothing but you can say probability distribution in some sense, right? If we are using nothing but functions, right? I'm not sure whether that how many activation functions have been covered. But if I talk about softmax, then it will be corresponding to probability distribution. And then I'm looking for the probability which is maximum, and we are getting that particular number 7. That means my model is saying it's number 7, and actually also I'm getting 7, which makes sense. Similarly, I can go for other values and check that what are my 10 predictions, what are the 10 actual answers, and then I can finally print the confusion matrix. Diagonal entries means how many times 0 was there and I have predicted 0, 957, which is good. How many times 1 was there and 1 was predicted, 1113, which is good. So if I am getting majority of the times diagonal prediction, I am doing well. But if off diagonal things are dominating, that means my model is performing bad. This is something in between that most of the times it's doing fine work, but many of the times it's predicting badly also, which is not good for me. So therefore, I need to do some kind of modifications. The first modifications, yeah, so we have enough time, so it's fine. Yeah. So first modification which I'm going to do is, initially I didn't consider any hidden layer. This time, can you guess how many neurons I have added as compared to previous time? In the previous iteration, 794 neurons were there in my artificial neural network. This time, can you guess the number? Anyone? How many total number of neurons I have considered for this model 2? And how many neurons are present in hidden layer? Hopefully you understand 784 neurons are present in input layer, 10 are in output layer. Why 10 in output? Because we have 10 classes, 10 predictions we would like to give. And you can guess the missing number, what it corresponds to. I would appreciate if someone can write this in the chat box, that how many.
Sir, it is
No,
115.
yes, yeah, absolutely. Right. So basically, 115 is nothing but one layer which we have added, which is nothing but again dense layer, but it is hidden layer. Why hidden? Because it won't be visible to us if we kind of follow the taxonomy of deep learning. Top to bottom, we are going, and we are towards the terrace, and then we are looking to downwards, and we are seeing how deep it is, and middle floors won't be visible. This is just like middle floors of our buildings, and it won't be visible. But if we just go through the process, then you will be able to appreciate that how nicely the accuracy has been increased just by adding this additional layer. But of course, it's coming up with the cost of a lot of parameters, but still, in terms of accuracy, we are gaining a lot. But this accuracy again won't impress me, because this is training accuracy. For us, testing accuracy matters, and test accuracy is 97.72, which is better, right? Which is good. This is good. Like, so basically, we have improved upon the previous result, which was 97, and this time which was 93. This time we got 97.71. So we are reaching closer towards 100, right? Which is good. Okay, fine. And this is one more variation of the same thing, that you can also flatten your input directly while you call the model. That's what rest of the things are same. That this is, we are not doing something new over here. This is just we are calling the flatten function over here. So this is nothing but how artificial neural network works. And in this case, it's working relatively better, mainly because of two things. Our images are black and white, and as you can see, only 784 pixels are required, which is a less number. What will happen if your number of pixels are more, like millions? We already know the issue with it. Your kind of number of I should say neurons and neurons. It's directly proportional to the parameters, which are nothing but our weights. They will increase, and the model won't be trainable. And the second limitation was, this is very much sensitive to locations. So since all the images are centered with respect to this particular grid of 28 cross 28, we are getting this nice result. But for different type of data sets where images are colorful, this model will fail miserably. I will try to showcase that part also very soon. But now let me just kind of explain the next important thing, which is nothing but the entire architecture of CNN, and then practically I will showcase how CNN will improve upon these existing results. So now the next thing is interesting where we talk about CNN. But again, for setup, some of the things which we have discussed with respect to implementation will be also applicable to nothing but CNN, I should say. So let's just directly talk about the architecture of CNN instead of wasting time over convolution, because we have already discussed it in detail. So the entire architecture, you will be happy to know that towards the end, we are going to have artificial neural network only. So the same code which we have written now, it will be also helpful to us towards the end of the model. But in between, we are going to have something which was not there earlier with respect to, I should say, artificial neural network. So what we are going to do now, we already know what is the objective of this convolution operator. It's nothing but basically trying to identify some kind of patterns, some kind of creation of feature maps. So why feature maps are important? So for example, consider the question like this. Let's say some kind of image is given to us, some kind of animal like koala is there, and we would like to identify whether this particular image is of koala or not. So then we would like to identify some kind of features like eyes, nose, ears, so on and so forth. And each filter is corresponding to some kind of feature identification, right? It can translate to some kind of mapping to some kind of feature, even though we haven't defined it. All these things will be done, will be taken care by nothing but I should say convolution neural network itself. But as an end user, we should at least know that what is the purpose of this filter. And again, it's a hyperparameter. I will decide how many filters I would like to have for this particular layer of convolution. So each, like I'm referring to convolution layer. So just like ANN layers, we are going to have convolution layers. But convolution layer contain two things: convolution, ReLU, and pooling. These three things together, it will be said as one convolution layer. And as you can see, I already explained these three things concretely to you. So now I just need to combine them. This three things together will call one convolution layer. And once we pass to one convolution layer, what we'll get? We get some kind of features like eyes, nose, ears. And now I am just appending one more similar kind of layer, convolution layer in this particular pipeline. What it will do? It will try to kind of capture higher order feature like eyes, nose, ears. They will combine and tell whether that particular image contains face of this particular koala animal or not, right? And similar to that, if I am having features corresponding to tails or legs, that will combine and tell whether that particular combination corresponds to body of koala animal or not, right? So those kind of things comes at higher order convolution layers. And if we kind of summarize all these things, and of course, towards the end, we are going to have, we need to again apply flatten, but this flatten will be significantly less heavier as compared to our original flatten function. Why? Because we have reduced our input significantly, and that's why I took a pain of creation of that particular visualization so that you can appreciate how drastically the input size will be reduced while we apply this convolution operations and pooling operations. And towards the end, our input will be very much less, and therefore ANN we can afford ANN towards the end, right? So that's the idea of it. So now if we just go through the core ideas, then as you can see, parameter sharing is one of the thing. What's the idea of parameter sharing? That whatever parameter with which or weights we are going to come up with respect to a particular filter, that will be across that entire kind of iteration, right? So the entire iteration will use the same, I should say, weights. So that's how the parameters is being speed up. ReLU, we already know that it's going to be fasten the computation because we are going to remove the negative numbers. We'll keep them zero. And pooling, I have already explained in detail. Overfitting is pending. I will explain it towards the end of the session because I would like to first showcase the implementation part. So with this setup, let's just try to go ahead and implement the same model which we have, sorry, I should say same data set which we have considered, which is nothing but MNIST data set. And let's see how we can apply convolution neural network over there and what it has to offer with respect to results. So now, if I'm not wrong, yeah. So this is the uh, uh, workbook corresponding to, again, the same MNIST data set. But this time, instead of ANN, we are going to apply CNN. So there is one myth that we can't apply CNN to black and white images, which is wrong. As you can see here, we have applied CNN. Just to motivate you, I am first directly showcasing you the end results, and then we'll go through the process, of course. So as you can see, 98.8 accuracy we got, almost very much close to 100, right? I should say almost 99 we got, and this too after just 5 epochs. Imagine what will happen if I run this for more epochs, which I'm going to do right now, just to showcase you what is the impact of epoch on final outcome. So let me try to create a copy of this also and share it with you so that you can appreciate this work, that how CNN can enhance the outcomes which usually we obtain with artificial neural network for this kind of setup. So let me just try to share this with you. Again, like I am doing, you should copy this notebook and modify the things on your own copy rather than this particular copy which I am sharing. Otherwise, the uh, kind of other people who are going to access it, they will struggle. So what you can do, you can just come to this file and then just click on this button, save a copy in the drive, and work on that particular copy. That's my recommendation. So yeah, let me just try to share this particular notebook with you so that you can understand how CNN works. So now let me just okay. So I will run this one more time, but before I run it, let me just try to again go through the setup. I don't need to repeat this 60,000, 10,000 trend test again one more time normalization, so I can skip all these parts. Right. The main change will come in with respect to nothing but our model setup itself. So again, we have applied this reshape. It's corresponding to nothing but flattening of the input, right? But we will do that over here also, as you can see, right? So this is nothing but I should say more like to make sure that our filter works properly. We are just doing reshaping. The main flatten for function comes over here, where as you can see, I haven't provided any parameter that what's my input size because I don't know that I need to go through my visualization and apply those formulas and in order to get the intermediate sizes or I should say in terms of feature maps, what's the magnitude of it? I don't know, but the model is intelligent enough to figure it out by itself. But let's just try to understand the differences. The first thing which we need to understand is what we are going to do in one layer of convolution. So as you can notice, every convolution, we need to answer three things. First thing is, what is our input? That is obvious, which is nothing but here I'm not changing my input, right? I'm not flattening over here, right? Sorry for this. This is just reshape. Flattening is happening over here just once. In ANN, we are doing flattening. Here, we are starting with our original shape only. This, as you can see, only change this reshape does is it creates this kind of I should say 2D to 3D, and in 3 dimension we have just one written over here, right? So basically, just we are doing this small change to look effective because usually when we talk about CNN, it's applicable to colorful images. So and RGB channels will come over there, but here we have just one channel because it's a black and white image. So that's the shape of our input. Now we need to answer the second question: how many patterns you would like to identify? That is nothing but our filters. So how many filters I would like to have? That is hyperparameter. There is no correct answer for it. You can ask, sir, why 48 has been selected? Why not 78? Right? You can go ahead and try 78. Deep learning, fortunately or unfortunately, it's not like our normal algorithms. Like if I talk about bubble sort, then all of you know that what are the steps required to sort numbers. But when we talk about this kind of deep learning systems, most of the things work based on intuition and practical implementation. So you can propose some kind of setup and convince others by showcasing that that particular setup is offering good results. That's it. So you don't need to provide formal proof of it because it doesn't exist. Okay. So how many filters I want? 48. What's the size of each filter? 3 cross 3. That is my hyperparameter. Again, I can change this. So it depends what level of filters I would like to find out. If my problem consists of some kind of different aspects, like where I would like to capture some kind of giant shapes, then I can go for some high magnitude of kernel also, right? So it's up to you. ReLU, you already know what's the why we know we need ReLU. And also at each layer, we would like to apply max pooling in order to reduce the amount of effort which we are putting towards nothing but I should say computation. And then we will repeat this process for the next layer also. But this time, since we have captured low level features in the first layer, I will be focusing on the high level features, and high level features will be emerged from the combination of low level features, I should say. So usually we should keep the number of filters less as compared to first layer. So therefore, I'm putting 32 over here. But again, this is not kind of hard-coded rule that every time you should reduce it. It's up to you. You can also increase it and try it. What's happening? Right? You can just see it. The rest of the things are extremely similar, as you can see. Right? And then we can see, right, we have just flattened the input, then we have just applied this one layer of 64 neurons uh, which will do processing on this feature map, and finally we will have 10 layers, I should say 10 neurons. Again, why 10? Because number of classes are 10, so we need 10. And this time activation function is softmax. So what's the idea of softmax? It's going to convert your final outcomes into nothing but, I should say, probability distribution. And now the loss function is also similar. The optimizer is also same. The matrix is also same, accuracy. And now I'm just going to provide the actual data, which is nothing but my training data in this particular case. And you can see after every iteration, straight away it's starting with 95% accuracy. And towards the end, it's getting 99.34 accuracy in training. And this is just after 5 iterations. And in testing, we are getting accuracy over here. So I need to call that evaluate function. So yeah, so evaluate function is over here. So you can see the result 98.8%, right? So it's significantly improved over my kind of nothing but the earlier model. So let me just try to do some modifications. So instead of, let's say, this 5, if I just go for, let's say, 25, and let me just rerun all the uh, kind of, I should say, cells, and see what happens with respect to this setup. So we'll come back to this and see what happens after 25 epochs with respect to this. So it will start straight away from over here. All the cells will be executed. So you can also try like this if you would like to do some kind of changes and check what's the impact of it. Right? You can just straight away check it. Meanwhile, let me just try to showcase you the real application of CNN with respect to some colorful images before we conclude, so that we can appreciate this work. So as you can see, straight away it's starting with respect to training. And let's just see. Let's just see. This is how it looks when the model is going to be trained. And
Sir,
this will
can you
also
tell me about sir batch size? You didn't mention about batch size.
No, in this simplest setup, I haven't included that particular parameter, but as we go progressively, we can include that also. Right. So for now, I haven't kind of included in my hyperparameters, but of course, it will come along with this fit setup. Right. You can also offer what it should be. So actually, the time is limited, and I would like to cover a lot of things. So therefore, I'm sticking to some basic aspect, basic minimum working knowledge of CNN first, and then if time permits, I will try to capture both these things, batching as well as overfitting towards the end of the session. So just give me 5 more minutes, and then I will take all the questions and we will discuss on it. So let me just go to one more kind of uh, workbook which I have prepared with respect to nothing but one set of data, which is nothing but in this particular case cipher10 data, and this is different. As you can see straight away, it's a colorful images, 32 cross 32 cross 3. So let me just try to give you one flavor of it, that how it looks. So if I just go to this, uh, just yeah, I will come to your question about overfitting. Just give me a minute. So let me just first demonstrate the impact of this CNN, and then I will talk about that overfitting thing also. So let me just try to showcase you this data set. So you can see it's a very complex data set. Its images are very tiny, and even for human eyes, it's very much difficult to differentiate between these classes. So if I just mm, try to open this only, so then it will make sense what I'm trying to say. So if I just, yeah. So as you can see, we have this type of images now: cat, deer, dog, frog, horse, ship, truck. And they are very tiny images. So many of the times we kind of confuse, especially images of frog and images of truck, right? So they look very similar, even though we can see some differences. Since the images are colorful, which is good, but the data set itself is very confusing because of its tiny nature. And now we are going to apply CNN and see that what's the impact of CNN on this particular data set, that how it's going to work. So as you can see, I'm skipping a lot of details over here just to save time. Let's just focus on the code aspect. So as you can see, we are going to divide our data, all the points, pixel values by 255 in order to make sure that all the values comes between 0 to 1. And then the key part starts over here. So as you can see over here, if I directly apply ANN, then what will happen? Still, it's a colorful image. So like I mentioned earlier, we should avoid ANN. But since the images are very tiny, extremely tiny, just 32 cross 32, we can just try and see what happens if we apply just ANN over here. So what I've done, we have two hidden layers of, I should say, neurons with 3000 and 1000 neurons respectively. Two hidden layers we have, and 10 is coming towards the end, which is kind of, I should say, a number of classes. And input shape is corresponding to nothing but my input. I should say, it depends upon nothing but number of pixels in my each image, which is nothing but 32 cross 32 cross 3. And then if we just go for 5 epochs, then we are getting accuracy of 46, and training accuracy is again, as you can see, 45.49%, which is not that good. Now let's just see the impact of CNN. What will happen if we apply CNN over here? And as you can see, I have kept 128 filters in both the layers of CNN, and kernel size, as you can see, 4 cross 4, which is the size of one particular filter. It's 4 cross 4. And input shape is as it is, 32 cross 32 cross 3. And let's just see the impact of CNN on this particular setup. So as you can see, if we just go for the evaluation part, first we are going for compilation. Let's say 10 epochs we are going. Accuracy is significantly better, as you can see, 78%. And if you go ahead and try to run this evaluate, then you will be able to see it will come around 60 around, if I'm not wrong. So which is significantly better as compared to our initial version, which was nothing but normal, I should say, ANN. So that's the power of CNN in this particular setup. So let me just try to share this also with you so that you can later on done this and appreciate it, that how good it is with respect to ANN. Meanwhile, I will also go back to that version of nothing but CNN, which we left and modified nothing but the value of epochs, and see what's the impact of that epoch. Meanwhile, let me just try to share this with you so that you can run this, right? So let me just go to this and make sure you create a copy of it before you run it. And yes, just a second. So okay, so let me just try to share this with you. Just a second. Okay, fine. So now let me just go back to some questions before I conclude. So one of the prominent question which is appearing multiple times, it's about nothing but overfitting. So let me just try to explain the idea of overfitting. Maybe I can just go to one of my other presentation. So this is also good. I thought that all the kind of relevant stuff has been covered already. So therefore, I skipped this. But briefly, if I can showcase, then deep learning is good for this kind of work, as you can see here. So image denoising and so on and so forth. So one more question is about ReLU and pooling. So ReLU is very simple. Like I was mentioning, if you are saying that some event is minus 5% probable. The other, it doesn't make any sense. Instead of that, I would like to say it's not possible at all. So I would like to convert that minus 5 into 0. So that's the purpose of ReLU. What it's going to do, all the negative numbers, it will convert it into 0. Otherwise, those numbers will come in between your computation. Those eventually, as you know, the flow of CNN, we are going to provide those numbers to ANN also. So those minus numbers, they won't contribute anything to the final outcome. So therefore, we are applying ReLU over there. And one more thing is asked is about uh, just a second, check that particular question, the most recent question which I am referring to. Maybe I can use one more device of mine. Yeah, so it's about max pooling. Yeah, so max pooling is just to reduce the computation. Like so, in closed neighborhood, I applied my filters and I got around 4 entries. Not all 4 entries are useful to me. I can just pick the maximum out of those four, or average out of those four. So representative, I should say, result survives with the help of nothing but max pooling. That's the use of it. But we can go for average pooling also. Any of the variation of that pooling function works. But usually we go for max or average pooling. So now if we go ahead and let me just try to see this. Yeah, so all these things have been discussed hopefully. So also the notation of this neural network has been abused a lot. So the most important parameter is weights, right? And that has been removed. So whenever you see this notion of uh, imagine that on this lines weights are there, and weights are not just there sitting over there, they are actually going to be multiplied with your input. So just like this session, that for example right now you are getting a lot of signals from this particular screen, from my voice, other signals from your personal life or your cell phone, right? Some kind of attention you are giving to all of this, and then you are going to kind of apply cumulative, right? You are going to apply weighted sum to all this, and then finally go ahead and take some kind of decision, right? So similar kind of thing we are trying to mimic with the help of this setup. So again, image denoising is one of the application. And now let me just try to focus on the question which was there, which was about nothing but overfitting. This was the idea of softmax which I was referring, that we just convert this 13 into 13 divided by 13 plus 12 plus 3. That's how softmax works, right? So that's one of the activation function which was referring to. And this is the idea of ReLU. Can anyone tell me which option is correct for ReLU? Option A or option B? If my input is K, then what will be my output in the context of ReLU? Minimum of 0 comma k or maximum of 0 comma k? What is your guess? Option A or
0,
option
Maxi.
maximum of 0 comma? Okay, so let's say if I am providing 5, then maximum 0 comma 5 is 5 and my output will be 5, right? Yeah, so correct option is option B. Right, thank you. So next thing, yeah, so let me just directly focus on that. So it's not slides won't be required for it. Without it, it will work with respect to overfitting. Yeah. So what's the idea of overfitting? Let's just try to understand the concept first, and then I will talk about the how we can resolve this particular issue of overfitting. So the core idea of, I should say, overfitting is sometimes the model works extremely well with respect to training data, but it fails miserably with respect to test data. It's like your student in the class, during the class sessions, he or she seems extremely intelligent, and he is gaining, let's say, in that during the classroom test, he's gaining around 95 out of 100, but in the end term examination, he is getting only 40 out of 100. Why that is happening, right? So you can guess the reason, right, with respect to student at least. Um, um, Now, with respect to data, something similar is happening. So let's consider a very simple problem. So what we would like to do is we would like to identify whether a particular image is of image of cat or dog, right? So let me just try to write somewhere so that you can get the flow what I'm trying to convey over here. So let me just try to go to over here. So even though we use this for some different purpose, I'm going to write my ideas over here. So let's say the problem is this. Problem is whether the image is of cat or dog. The simple problem we are trying to solve with the help of using, let's say, CNN or ANN, whatever we would like to apply. Okay. Now, what is the issue over here? let's say in training set, we have lot of cats, but all cats are sitting on sofa. So over the period of time, what will happen? Over the period of time, uh, model will focus on features or presence of sofa. So as soon as it sees sofa, it will say the cat is present. Right? So sofa implies cat. This is true in training, and therefore it works absolutely fine. So for example, in the classroom setup, let's say every semester you are using the same set of questions, and student who is performing extremely well, somehow he had access to all those question papers along with answers. So therefore he is performing very well in the classroom. But at the time of testing, what is happening? There are some dogs who are sitting on sofa. So now what is the issue? The model will see the sofa and it will straight away say sofa implies cat. So therefore image contains, model will predict it's nothing but dog, but actually it's cat. This is called overfitting. Why this is happening? There are some extra smart neurons, right? Kind of overlearned, right? And they are focusing on noise or unwanted patterns, which are not related to, I should say, not related to the problem itself, right? Or core idea, I should say, core aspect of the image itself. Right? Just like, let's say, every year you prepare a question paper, and the very first question of your question paper is true, false, and the answer of the first three is false. And that is happening since last 10 years. So now what students can do, they can just focus on this pattern and straight away, without even reading those statements, it can say that first three must be false. This is called nothing but overfitting. Now, how to solve this? That is the question. So somehow, so it's like in the classroom, let's say some noise is coming up, then what you will do? You will punish some set of students, right? And you will say that please go out of the class, right? And you may randomly select 5 students and say get out of the class. And you will do this repeatedly for, let's say, consecutively 3 to 4 classes. And then you will suddenly notice that now class is paying more attention, right? Why? Because in the process of kind of removing the students from the class, there were nuisance values in the class. They were also kind of removed. The similar thing we are proposing with the help of, in the context of, I should say, deep learning systems like ANN and CNN, which is called dropout. What's the idea of dropout? After every epoch, remove some unwanted, right? Remove some portion of neurons, disconnect them from the network, and network will relearn without them, right? Just to make sure that we don't kind of give too much importance to some small segment of our neural networks. And this is also good for, I should say, in some sense, sharing of weights. Okay? So that's the core idea of dropout, which we usually use. Okay, so hopefully the idea of overfitting and one of the resolution is clear. Before I conclude, right, so there are a couple of questions pending. I will just go through them, and I have one more session, so I will make sure that I answer it in that particular segment. But before I conclude, I will also go through some more questions and try to answer a few of them right now. But before I conclude, you can see that there is direct impact on epochs also, right? Usually, if a model is not, of course, overfitting, then uh, if your training accuracy is good, then usually training your testing accuracy will be also good, right? So in this particular case, what is happening? You can see just after 17 epochs, we have reached to this particular level, 99.84. So therefore, many of the times, yeah, so it is very close to 100. That's we saw very briefly for 1 second, like one in accuracy, and corresponding loss is also kind of reducing as we move forward. And once this part completes, we'll be able to see what is happening with respect to prediction aspect and what is the accuracy of prediction. And then we'll be able to see some massive improvement with respect to prediction for sure because of these changes. And of course, you can try with a lot of things like there are a lot of other hyperparameters. Like for example, we can just go this important prompt over here just to summarize whatever we have discussed over here. We create a nice like let me just say info graphic which captures all the important hyperparameters uh, required, setups required for implementing ANN and CNN, and ensure you include uh, ideas of optimizer. Then we have talked about, apart from optimizer, loss functions. Then we have talked about epochs. Then we have talked about dropout. Then we have talked about nothing but which is pending, which is nothing but patching, right? All these are nothing but hyperparameters. Apart from that, more important hyperparameters are nothing but filters, right? Apart from that, what is the size of kernels, right? Kernel size, right? All these are nothing but our hyperparameters, and they will be the nothing but differentiating factors with respect to our outcomes, right? So number of neurons, right? All of these are uh, let's make sure it looks visually good and useful. Okay, so let's just see this particular visualization. It will take around a couple of minutes to come up with it. Yeah, something went wrong. Okay, so let me just try to copy this so that yeah, I can we can kind of utilize it uh, afterwards also. Maybe I can just paste this to some other system just to see what it does, right? So maybe I can go to Gemini also for the same. Yeah, let's see. Okay. So and then we'll be able to summarize this findings very smoothly, because as a developer, as a programmer, you must know that what are the controllables at your end, right? Once you understand and appreciate the architecture, now it's all about how intelligently you can come up with some configurations which can solve the problem. Of course, there are many other things with respect to these technologies, like the entire new domain on which, relatively new domain, I should say, is a graph neural network, which is again very much inspired from CNN. Because if we talk about the data which appears in the terms of graph, let's say the data of Facebook or data of LinkedIn, where each person is nothing but one node, and if one person follows another person, then we are going to put an age between them, right? So those kind of data we can't apply traditional CNN, and then we have to transit towards graph neural network, and that is also kind of a fantastic domain where kind of I am working since last 5 years. And basically it's up to you, means how you are going to utilize it, but it's a good starting point. And also we are it's just second day of the FTP, a lot of things are going to be covered. And apart from that, what I would like to highlight that one more kind of branch, apart from, I should say, this ANN, CNN, transfer learning is also one of the interesting things which you should learn. But yeah, I guess that's it from my side today, because time won't permit me to discuss much. Let's just see this particular visualization uh, before I conclude. So as you can see, let me just try to save this, and we just see this and appreciate it before we kind of conclude. So it has been saved, but yeah, it's saved within this ecosystem of Gemini, if I'm not wrong. Let me just try to download so that I can just zoom this and we can just see this. Uh, just to kind of solve a couple of your doubts, I have created this because time was slightly less, so we can just appreciate the power of generative AI also, because this is also one of the themes of FDP, and in my second session I will be talking more about it. So yeah, so as you can see, one query was about epochs. So now it will be clear from this full passes through the entire training data sets, right? So that is corresponding to one epoch. One more query was about over here, what is batch size. So as you can see, number of samples per gradient update, that is all that again, it's corresponding to you. Hopefully this will become clear if I can briefly showcase you this particular visualization or image of mine. Yeah, so over here, what we would like to do is, after repeated updates of I should say, just a second, let me just try to find out that particular interesting image, and then we'll discuss more. Yeah, so basically this is kind of nice surface of different, I should say, weight combination, and with each weight combination, what is the corresponding loss? And definitely this is not money, this is loss. So we would like to not minimize the loss, we would like to make I should say, sorry, we would not like to maximize the loss, we would like to minimize it. So what is the idea of this gradient? What we need to do, imagine a scenario that you are going to kind of pour some droplets of water on this particular surface, and wherever water stabilizes, we would like to reach that particular place. And exactly that we are doing with respect to this, I should say, item optimizer. And learning rate will decide that how fast, how aggressively we will try to aim for that particular minima. So if learning rate is too high, learning rate is also one of the most important hyperparameters. If it is too high, then maybe we overshoot the minima, right? So we miss it, right? Because we are changing our weights very rapidly, which is not good. If it is too less, then we will reach towards minima very slowly. That is also not effective. So something in between is good, and there are some other strategies also which will kind of fine tune it. But usually, Adam Optimizer will take care of this. There are various decay schedules which will ensure that we will kind of reach to this minima properly, right? So, for example, some strategy can be initially learning rate, we will keep it static, and afterwards, after some epochs, like after 10 epochs, we are going to decrease the learning rate exponentially, right? So those kind of things we follow, right, with the help of this decay schedule. So now the next thing is, yeah, just before I conclude, let's just see and appreciate what ChatGPT has to offer with respect to this setup also. So yeah, so this is the visualization with respect to ChatGPT. Let me also try to download and appreciate what it has to offer. Side by side, both are upcoming, which is fantastic. But at one time, I would like to focus on one. So maybe I can just focus over here. So you can see, right? So all these things we have discussed. So number of hidden layers, number of neurons per layer. But CNN hyperparameters, let's just focus on it. So you can see convolution layers, usually 2 to 6 plus, filters 16, 32, right? And strategy can be different also, right? For this problem, it's suggesting increase with depth. I was suggesting reverse, so it depends upon your problem. You can go both ways. Kernel size depends. Slide padding, you already know about it. Pulling, you know about it now. Full connected head, right? So again, after flattening, dense layers are going to be used. Dropout, right? And then good starting point usually for 3D images, we are going to apply convolution, value pulling, convolution, value pulling, then flatten the input, then dense layer, and then finally we are going to get the output. And this is how this differs from ANN. So I like the structuring of um, ChatGPT better because it puts this thing side by side, which makes sense. And of course, there are many other things which I couldn't cover, but I guess in this time I tried my best to capture the core ideas of CNN properly at least. And I've already shared most of the things, and I will try to share the remaining things with you very soon. Yeah. So that's it from my side. Yeah. Thank you.
Okay. Participate, if you
Yeah,
have any
and
questions, you can ask to sir.
yes. We can go ahead for the questions, and also I will just share my contact details. So in case of any other questions, or you can just contact me on my email address, or maybe connect with me on LinkedIn if required. Yeah.
Sir, I'm Balagopalakrishnan, one person. So when we do the convolution, so you were saying that only 2D we will do for filtering. We will do that 2D instead of 3D, even though the 3D is used.
No,
So
yeah. So filtering will be done on at level 3D only, but we will view it as a 2D. That's what I was saying. Because the filter depth is equal to nothing but the depth of our input. So it will take care of that particular third dimension. We don't need to do. We are not kind of like, so if I just go to this particular visualization of me, then it will become clear what I'm trying to convey. So in 2D, if we just reiterate, in 2D, what we are doing, we are changing rows also. We are also changing, in some sense, columns. But with respect to 3D, what I am saying that we are not going to change the depth. We are going from left to right. We are going from top to down in 2D. But in 3D also, we are going to do the same thing because the depth of the filter is same as the depth of the input. That's what I meant. So, for example, if I just try to go to that particular demonstration, yeah, if I can find it out very quickly. Yeah, so it will come over here somewhere. Yeah, so so over here, if you see this particular thing, so yeah, so maybe even we don't need to even go to this segment. Over here, it will become clear. So you can see we are going from, if I just play this, then we are going from left to right, top to bottom. So imagine in 3D what will happen. We will get one more dimension, which is nothing but depth, and that dimension is, let's say, 3. So 6 cross 6 cross 3. But again, what will happen? The filter depth will be 3. So therefore, it will look like this only. That's what I'm saying. So effectively, we are doing 3D, but the approach is like 2D only. That's what I was conveying. So it's not like that we are doing in 2D, doing in 3D only, but since the depth of the filter is same as depth of our input, we are getting the flavor of 2D only in 3D. That's what I was conveying. Okay. So hopefully it is clear. Yeah. Okay. So any other questions? Okay. Okay. Fine.
Yes, sir. Thank you so much, sir, for delivering such an informative and engaging session on convolutional neural network. Your clear and insightful explanation and practical implementation of CNN convolutional activities such as 1D convolution, a 2D convolution, a smoothing, pooling, different type of activation function, CNN architecture, and their real-world application made the concept easy to understand.
Thank you.
We sincerely appreciate the time, knowledge, and expertise you share with us on behalf of Dr. Vaskar Mandal sir, Dr. Mukesh Kumar sir, and all the participants of their faculty of this faculty development program. I extend our heartfelt gratitude to you. Once again, thank you, sir, for your wonderful session. We look forward to learning from you again in the future. Thank you so much, sir.
Thank you, ma'am. Thank you.
Hello, sir. Hello.
Yes, sir.
I'm audible, sir?
Yes, I guess Aditya ji.
Yeah, I have a question. Yeah, I have one question. Sorry to interrupt.
Yes, sir.
The question is that like we are using epochs and learning rate. So in normal simulation, if we are doing a numerical simulation, we are using a step size. So it is epoch we can consider similar to the step size, or how we can interpret it.
So it's like we are saying the model that go through the entire data, whatever we are providing. It's kind of iteration in some sense that we are giving the entire data one
Number of
time to
iteration
our.
we are also giving in numerical simulation. It is similar to that.
In some sense, it's similar. Yeah, similar.
Okay, okay. And what about
But
the learning rate?
learning rate is different. Learning rate is about how aggressively you are trying to kind of reach towards minima. So how fast you are changing your weights. That's the kind of parameter corresponding to learning rate. It's the meaning of learning rate. So if you keeping it very high, then your weights will change rapidly. But in that case, you may overshoot, like I mentioned. And if you keep it too low, then you have to run your system for multiple effects. So you have to kind of fine tune it. Right. So again, these are, like I was saying, it's these are experimental things. So there is no concrete answer for it. It depends upon your data set, your setup, and a lot of things go together, like including loss function. That will also decide how nice your model will work, right? So it's a combination of things, but all are important. Yeah.
Got it. Got it. Thanks a lot. Thanks a lot.
Thank you, sir. Thank you.
Yeah. Good morning, ma'am.
Madam, can you hear me? Madam, it seems you are muted yourself. Am I audible? Can anybody confirm me?
Yeah, sir, you're audible.
फर्स्ट गेट से इस लैब में जाओ, राइट हैंड में देखोगे ना मेरा फोन. Madam, you can switch off your camera and you can try.
Am I audible now?
Yes, yes.
Okay.
Okay.
I'm
I
audible
am
now?
asking Shushmita to introduce Madam. Please, Shushmita.
Okay. Thank you. Sorry. Yeah. Okay. Is my screen visible?
Yes.
Bhaskar?
Yes, I can see your screen.
Okay. Should I start or wait?
Ma'am, your introduction is going on. So please give us 1 minute.
Okay, sure. I would like to mention that it is truly impossible to introduce Parna Sahaman's remarkable academic journey and achievement in just 1 or 2 minutes. However, it is my pleasure to introduce our esteemed speaker for today's session, Dr. Sparna Sahawan. She is currently working as an assistant professor in the Department of Computer Science and Engineering at IIT Patna. Ma'am earned her MTech and PhD from the Indian Statistical Institute, Kolkata, and has over 15 years of academic and research experience. Her research interests include artificial intelligence, machine learning, natural language processing, multimodal information processing, and text mining. Ma'am has supervised over 18 PhD students who have successfully graduated under her guidance, and currently she is supervising over 13 PhD students, and many scholars under her research group received the prestigious Prime Minister Research Fellowship. Ma'am has authored more than 400 research publications, and she received several prestigious awards, including the Google India Women in Engineering Award, the SCRV Women in Excellence Award, Young Achiever Award, and many more. We can't list in the number. She is also listed among the world's top 2% scientists in artificial intelligence and image processing. Today, Ma'am will be taking the theory session on generative AI, theory and ethical issues. With this brief introduction, I extend a warm welcome to Dr. Sriparna Sahawan and respectfully request you to take over the session. Over to you, ma'am. Please continue the session. Thank you, ma'am.
Yeah, thank you, Bhaskar, for this invitation, and thank you very much for the nice introduction. So yeah, so today I think I have this 12 to 1 session and also the afternoon session. So in the afternoon session also there is a theory session and followed by some demonstrations. So yeah, so in the morning session, I just want to introduce, I think the previous speaker was also talking about this generative AI. So I will briefly talk about the generative AI and also their biasness, because generative AI tools and techniques are very useful. But in recent times, many researchers are working on biasness studies of generative AI. So this research area is becoming very popular nowadays. So I want to show you some of the interesting studies, like how that researchers basically found out that these LLMs or the VLMs, they have some kind of gender bias, they have the racism bias, they have some kind of popularity bias or the object bias. So some interesting observations I really want to show you, so that you should not blindly trust the outputs of these generative AI tools and techniques. So yeah, so basically recently we have also just developed our new research team called the Drisha. So our lab, in IIT Patna, we have a lab called Drisha. So Drisha is a amalgamation of two terms, Drishti plus Bhasa. So Drishti means vision and Bhasa means language. So all my students are working on different topics of natural language processing, but one theme is very common, that is the multimodal information processing. So for all our tasks, our aim is to fuse data coming from text and images. So we are not only relying on the text data, but also text plus image together. Okay, because nowadays social media data or the newspaper data, all or SMS, everything is becoming multimodal. So you can also visit my webpage www.iitp.ac.in /Sriparna, and there is a resource page also. So many my students are also developing resources in Indian languages, because in Indian languages there are many medium resource languages and low resource languages. So my research lab is not only focusing on developing algorithms, but also developing many resources. So you can also visit my webpage and download the datasets which are available freely, and you can use them for your further research purposes. So yeah, so starting with the LLMs, you all know that nowadays we cannot think about our life without LLM. ChatGPT has become part and parcel of life, or Claude. Gemini is giving a summary of our emails. Like whenever we have a common, like nowadays Google has integrated Gemini with Gmail, and before opening an email, we are getting a summary of the email. So, what is this large language model? So large language model is basically a deep learning model, and the transformer is a backbone. So obviously transformer is not the movie Transformer, but in 2017, Google researchers came up with this idea called the transformer, which is a deep learning model. There are two different modules. One is called the encoder, and another is called the decoder. So encoder basically encodes the text data, and the decoder is generating the data. So transformer module is widely used in the machine translation, natural language generation, summarization. So yeah, so that is the backbone of all these large language models. And why this is called large? So this large is because of huge number of parameters which are there. So parameters mean the weight values, because these are neural networks. So, in neural networks, there are different neurons, the basic building blocks of neural network. There are multiple neurons which are mimicking our brain-like structure. In our human brain, there are many neurons. Neurons are connected, and they are doing the message passing, and they are basically controlling all the operations of our body. And similarly, neural network is also mimicking the human brain structure. So there are many neurons, and neurons are connected by some weight, by some edges, and each edge is having a weight value, and these are called the parameters. So these large language models are not only having huge number of parameters, but also, they are trained on huge amount of data. So they are large in two sense. One is their number of parameters are huge, and also they have a huge number of data sets by which they are trained. And like you can't imagine that there is a statistics that if suppose there is a 15-year-old kid, and the amount of data they have seen in their storybooks and the other books, that is so if you will just sum up all the data, so the data which is used to train these LLMs are much higher. Okay, and all the companies nowadays are focusing on developing their own LLM. Like OpenAI was a startup from some Stanford graduates, and Google, Gemini, Google, Anthropic, DeepSeek, which is a Chinese-based startup, all are now trying to develop their own LLMs. So this is a study. You can see that so many LLMs are available in the market, that we are mostly categorizing the LLMs into two categories. One is having less than 100 billion parameters, and another is having more than 100 billion parameters. Okay, so for example, GPT-3, Jurassic 1, MTNLG, Palm, Palmy, GPT-4, all these models are having more than 100 billion parameters. And if the models are having huge number of parameters, we cannot store, we cannot keep them, we cannot it's very difficult in the academic setup to store them in academic server, and to fine tune them with the huge amount of data. But comparatively, this Elmo, GPT-1, BART, Robata, all these models are here less in parameter size, and we can easily store them in the academic setup, and also we can fine tune them with the available amount of data. So this is the history of the generative AIs. You can see that it started with the Turing test in 1950s. In computer science, we do not have Nobel Prize. But in computer science, that we have a Turing Award. So every year, there are some 2-3 scientists who are doing, some recommendable works in the computer science. They receive the Turing Award. So and that is in the name of a scientist called Turing. So in 1950, Turing basically invented this Turing test. So what is this test? So basically, he mentioned that suppose in a room, there is a partition or there is a curtain in between the room, and in one side of the room there is a machine and there is a human being, and either the machine can generate some text or the human being can generate some text. Okay, and beside the curtain on the other side of the room there is another human being, and now there is maybe a display board, and this display board is displaying what the on the other side of the room, what the human being is generated or the machine is being generated. So the second human being who is in the other side of the room, he or she has to judge whether the written text, whether the displayed text is generated by the human being or from the computer. Okay, so if suppose the human being is not able to differentiate or distinguish properly between the human generated text and the computer generated text, then the computer will win. Otherwise, if the human being can easily differentiate between these two texts, then basically computer loses. That means it is very easy. That means the computer generated text is not at par with the human generated text. That means there are some easy patterns by which a human can easily differentiate between the human generated text and the machine generated text. So that is the Turing test. And in 1956, AI researchers, basically this AI term is first coined in a Dartmouth conference. Okay, so every year the AI researchers, they started organizing this Dartmouth conference, and whatever inventions were done in the field of AI, they used to discuss this in the Dartmouth conference. From 1980s, AI researchers started working in the field of expert systems. So if you are working in a hybrid systems, like maybe integration of multiple algorithms like neural network plus SVM or feature selection plus SVM, so integration of multiple algorithms is called the expert systems. 1997 is very crucial in the history of AI. IBM developed this, Deep Blue, which is a reinforcement learning based chess player. It is a AI based algorithm, and which basically beats Gary Kasparov. Gary Kasparov was one of the best chess player at that time, and this AI algorithm was able to outperform, was able to beat Gary Kasparov in chess playing. From 2012 onwards, there is a huge interest in deep learning, because in between NVIDIA also started basically develop the parallel processing architecture and the GPU architecture. So, in order to train deep learning algorithms, we need some huge computing facility. So as NVIDIA has come up with the GPU architecture, so from 2012 onwards, researchers started working in the deep learning. So there are many algorithms developed in the computer vision field, like DenseNet, AlexNet, VGGNet. All these big, these are called the pre-trained models, because these are already trained on huge amount of image data. So researchers, computer vision researchers were also trying to build some data sets which are huge collection of images for different tasks of images, like image segmentation, image capturing, okay, all these tasks. And with these data sets, they try to train the huge like CNN architectures, and this AlexNet, VGGNet, DenseNet, all these architectures are developed. And also in the NLP field, in order to understand the long context, like if you have a long sentence, it's very difficult to understand the meaning of such long sentence. Like suppose you have a sentence like the chef who has worked for a long time in Delhi has started his own business in Patna. So here started, so this refers to the shape. This is called the long-term dependency. So if you want to understand the meaning of such long sentence, you really need to, this is called, you put attentions. Okay, so researchers come up with the idea of long short-term memory, gated recurrent unit. All these deep learning based architectures are invented during this time period. And from 2020, this OpenAI was before that only OpenAI was invented by some startup, by some graduates of the Stanford, and then they understood that now as GPU facilities available, and we also have the deep learning architectures available, transformer architecture is available. So now it is high time to gather huge amount of data which is available in the internet. So basically, OpenAI researchers, they started gathering all the online data, like all the storybooks, all the Wikipedia data, all the newspaper data. They started collecting, and by after some pre-processing, they started using this data to train these huge transformer networks. Okay, so GPT-3 was invented in 2020, and GPT-4 and ChatGPT. ChatGPT is such a good interface that without knowing the Python or any programming language, in natural language, you can give the instruction to ChatGPT, and this is called the prompting. And now ChatGPT can easily execute your instruction, which is given in natural language. So that is the beauty. So for common people, now AI became so affordable, and people can easily use the AI algorithms or the AI softwares. Now from 2025 onwards, researchers started working on the agentic architectures. Now a single LLM is not enough. So initially, if you want to solve a complex problem using LLMs, as a human being, you only have to decompose the problem into sub problems, and maybe in the prompt only you have to mention the instructions for solving all the sub problems. But in a agentic architecture, agent can plan, and then agent can use many tools to execute all these plans. So so from 2025 onwards, researchers started working in the agentic architecture, and now you only have to give an instruction, like for example, plan my holiday in Thailand, and then this agent will do everything. It will check your calendar, it will check your availability in the calendar, it will apply for your leave in the leave portal, it will call some tool like Make My Trip, it will check for the flights, it will book the hotel, it will book the ground transportation, it will make all the arrangements like your itinerary, it will make what are the places you will visit in Thailand. So everything, all the plans it will do. So you do not have to decompose the task into subtasks. So those will be done by different tool calling or by different LLMs inside the agent. So yeah, so this is more detailed history of generative AI. So already I have discussed few, like whole computer science history in a nutshell. So during 90s or up to 1948, it was mostly the era of hardware computer science. Mostly researchers were that time building computers. So they were mostly focusing on how to build CPU, or how to build the vacuum tube. They were mostly, research was mostly on digital logic, cybernetics, in those fields. And as I mentioned that in 1950, Alan Turing, he invented this Turing test, so that we can easily separate the machine generated text versus human generated text. Now the AI term was first coined in a Dartmouth proposal by this John McCarthy. So this John McCarthy is called the father of AI. So there was a paper called the Dartmouth proposal, which is presented, in which for the first time the AI definition is used. Now, starting from 1957, the neural network concept was proposed, and also researchers started working on the fast AI program. The ELIZA chatbot was also developed. Now, during 1980s to 1989, researchers were mostly working on the artificial neural network, convolutional neural network, etc. In 1986, the backpropagation algorithm was developed, which is used to train the neural network. So this is a multi-layer networks could learn non-linear mapping, significantly contributing to the field's progress. Now in 1997, the Deep Blue, which is a IBM's chess player, it defeats chess world champion Garry Kasparov. Now in 1994, from 1994, researchers were mostly working on, again, the deep learning. LSTM neural network was designed in 1997. During, you can see that in between there are some winter means not much progress has been made in the AI field, like from 1973 to 1980. This is the first winter. 1987 to 1993, this is the second winter. So then Apple Siri, this was a fast chatbot made by Apple. It was proposed in 2010. Then in 2012, AlexNet, which is a huge CNN-based architecture which can perform all types of computer vision-related tasks. A revolutionary deep learning architecture significantly outperforms ImageNet. And ImageNet is a huge data set which has a huge collection of images and all the tasks. Now the transformer model is proposed in 2017, and here researchers, but these Google researchers, and one Indian was also, the first author was an Indian, Bhasini. So Bhasini Etel, and there are many other researchers from Google. They came up with this transformer architecture, and which is the backbone of all the other LLMs. So there is one encoder module and there is one decoder module. So the encoder module is responsible for encoding the text, and then the decoder module is responsible for generating some text from the encoded output. Now here there is a concept called the self-attention. So given a sentence, maybe all the words are not equally important. So you need to focus on only few words. So okay, so this is called the self-attention. Okay. So for example, in a sentence there are many stop words, there are many prepositions, there are many articles, there are verbs, there are some proper nouns. So in order to understand the meaning of a particular sentence, maybe you need to focus on only some keywords. So this is called the self-attention. So this concept was first introduced in the transformer module. So then, why these transformer modules, and why researchers can they think of this transformer module, and also they are capable of training the transformer module with huge amount of data, because before that, this NVIDIA came up with this GPU architecture. So before that, Python based packages like TensorFlow, all those were invented in 2015, and and those are only, in TensorFlow almost all the Python library functions are available. Like LSTM, GRU, all these library functions are easily available. You can simply call those library functions and you can apply them on your data. So once the transformer is invented in 2017, now all the big companies like Google, Meta, all these companies started developing some language models based on the transformer. So their main task was to pretend the transformers on a huge amount of data and make it available for the researchers. Now researchers have started using this pretend model for either generating some embeddings. Embedding means that, see, computer cannot directly take a text, because a computer only understands, the binary numbers. So you need to convert the text into a vector, and then the vector can be converted into a binary number. So this process is called the embedding generation. So GPT-1, BERT, GPT-3, all these are basically, processes of embedding generation. Now, in 2020 is called the 2020 is also very important in the history. So this is here the diffusion model is invented. So diffusion model means you just give a prompt and some images are being generated. So basically, you can give a so basically it is text to image generation. So the task is more difficult, because till now by the use of transformer only text is being generated from text, but by the use of diffusion model, now from text to image generation is also possible. And then in 2022 is another important year in the history of AI, because OpenAI introduced the ChatGPT, which is an interface, and now we can give a command line, we can give a simple prompt in natural language instruction, and this ChatGPT can also produce some output in natural language. So, and from 2020 also, there are many important inventions in the robotics field. Tesla introduced the self-driving car. As there are so many inventions in the field of AI, like there are so much progress made in the robotics field, so much progress made in the generative AI field. There are many misuses of these AI technologies. So that's why, AI researchers feel the necessity of making some ethical guidelines on the uses of AI. Okay. So AI researchers first discussed that there should be some regulations and the ethical guidelines on the uses of AI tools and techniques. In 2024, European Union first came up with the AI Act, that they first mentioned that whenever some researchers has to submit a research proposal or some grant proposal, he or she has to follow all these AI acts or the AI rules and regulations. Okay, there are some ethical guidelines. For example, if you are working in the healthcare domain, so you can obviously work on helping the doctors, but your AI algorithm cannot simply replace the doctors. Okay, it could be a helper to the doctor, but you cannot aim in replacing the doctors. So this kind of AI rules and regulations are invented. And then from 2025 onwards, so see, till then, like ChatGPT or this GPT 3.5, all these models are very good in generating text, summarizing text, writing essays, or question answering. You can ask any general knowledge based question, and these models are extremely good in answering those. But if you simply ask this GPT-3 or GPT 3.5 some JEE advanced mathematical question, these models will face some difficulty in answering those advanced level mathematical questions. Or if you give some logical, very high level logical questions, or if you will ask these models to, submit your income tax, then also maybe these models will face some difficulty. So but then from 2025 onwards, there is a DeepSeek company which is based in China. So this DeepSeek company, they basically develop some reasoning models. So what is a reasoning model? So reasoning model means that now a model can also reason, like think. It can generate some thinking process also. Okay, it can generate some thinking process, like it can decompose the task into some many subtasks. Okay, and then it can solve those tasks. So that is the DeepSeek. The Chinese DeepSeek overpasses OpenAI in 2 weeks. So it can decompose the task into subtasks, and then it can solve the task. Now from 2025 onwards, researchers are mostly working on, this agentic AI. As I mentioned that now LLM can plan and also call many tools, external tools, and then solve the task. You do not have to, as a user, you do not have to decompose your task into subtasks. You simply give a prompt, a single prompt, and depending on the complex prompt, it will decompose, it will plan how to execute the task, it will call many tools, and it will execute the plan. So you can see that almost every year, so since the very beginning, after the invention of transformer, almost every year, almost all the companies have developed, every month at least, you can see from this figure, every month there is a new LLM which is being introduced by different companies. And some LLMs are open source. Open source means you can freely download them, and you can easily fine tune them using your data, and you do not have to pay anything. Their weights are available. And some LLMs are closed source. For example, these nowadays the GPT models are all closed source. You have to buy the key and then only you can get the models. Okay, so basically this is the chronological display of the LLMs. So models on the upper half are the open source models, and the bottom are the closed source models. So the most important part of this LLMs are that they are few shot learners. Like, because LLMs are already trained on huge amount of data, millions of billions of data. So you only have to supply them. Like, suppose you want to solve a new task using LLM, you do not have to train it again. Like what we used to do in a machine learning paradigm. Like in a machine learning paradigm, whenever there used to be a new task, we had to train the machine learning algorithm with the new training data. Okay, so we have to again build the model using the new training data, and then has to test the model on the test data. But now that scenario has changed a lot, because this somehow this language models have some general intelligence. Okay, so they are somehow general purpose model, and they have a very good kind of intelligence. They have intelligence about almost all domains. Okay, so whenever you are asking it to solve a new problem, you only have to show a few examples of the new problem. Okay, this is called the few shot prompting. You simply show it few examples of the new problem, and then only the model can start solving the new problem. So language models can be viewed as few shot learners in the sense that they can generalize to new tasks and domains with only a few examples. This is because language models are trained on a large corpus of text data, which provides them with a general understanding of the structure and patterns of language. So basically, this is the paper, Language Models are Few Shot Learners. And in this paper only, they have somehow proved that yes, we can easily use a language model, and language model can be used to solve the new task. And this is also, there is a new name for this. So this is called the in context learning. Okay, so in context learning means that you simply show a few examples of the new task, and then from there it will start solving the new task. Okay, so you do not have to again train the LLM for the new task. You only have to show a few examples of the new task. So this is called the prompting also. So see, the for LLMs, you can give the instruction in natural language, and this is called the prompting. Okay, and there are different ways of writing the prompts. So prompt engineering is a technique used in NLP to improve the performance of language models. And if you are interested in learning more about the prompt engineering, you must read our survey paper. So, we have written a survey long back in 2024 when LLMs just were becoming very popular. So, but this paper became very, very popular already, though we have written this paper 2 years back. But now in the Google Scholar, almost it has 2000 citations. So if you are interested in understanding what are the different types of prompting techniques available, you please read our paper, A Systematic Survey of Prompt Engineering in Large Language Models, Techniques and Applications. So, prompt engineering is really a very important topic. Because if you are changing your prompt, maybe there will be some change in the output. That's why you have to give your prompt in a very precise way, so that LLM can easily understand your instruction well. Okay, so prompt engineering is now a very active research direction as well. And I will now showcase you some of the important ways of prompting the LLMs. Now, so obviously these are the few important prompting techniques. One is called the zero shot prompting. So in zero shot prompting, we only give the instructions, but no examples of the task. For example, suppose the instruction is translate English to French. Okay, so we are asking the LLM to translate from English to French. This is the instruction. and then the word in English is cheese, and we are asking the LLM to translate this cheese word to French. Okay, this is called the zero shot prompting. Now, one shot prompting means that again we are giving the instruction translate English to French, and then we are giving one example like sea otter is translated to lottery de mar. Okay, this is an example we have given, and now we are asking that you please translate cheese to French. Few shot prompting means you give the instruction, and then not only one example is sufficient to understand the instruction, maybe more than one examples you just show. Like sea otter to translate to lottery de mar, peppermint translated in French to mentry poivre, plus giraffe is translated to giraffe, peluche, and now you are asking it to translate, cheese to English. Now, there is another way of prompting, which is called the chain of thought prompting. So, chain of thought prompting is important in the reasoning. Like I talked about this DeepSeek R1, and nowadays there are many such R1 models, and these R1 LLMs are important when you are trying to solve some complex mathematical problems or some logical problems, where basically you are not only interested in getting an output, but also how LLM is, generating the outputs. Like you want to also see the thought process. So suppose there is a mathematical problem, and maybe LLM is generating the output. Okay, that is fine. But maybe you also want to see the all the sub steps that it is taking to generate the output. So the chain of thought is prompting is very important when you are suppose asking the LLM to solve a mathematical problem, and in order to solve the mathematical problem there are many sub steps that the LLM has to take. So in the prompt only you are mentioning about all these sub steps. So in the LLM has to basically take compute all these sub steps, and then finally has to come to a conclusion. So this is the thing in the right hand side you can see a a thread like structures, like from input to output there is a path. So in between in the path there are many cycles, and you have to basically execute all these path. Now, tree of thought prompting is that it extends chain of thought prompting by managing a tree structure of intermediate reasoning steps known as thoughts. Each thought represents a coherent language sequence moving toward the final solution. So here, basically, in the tree of thought prompting, you can see that maybe sometimes in order to solve a mathematical problem, we have multiple ways of solving that. Okay, not only a single way, but multiple ways. So in that case, we can take multiple possible path and can come to a conclusion. So in tree of thought prompting, we can enumerate all such possible paths. Now, there is also self-consistency. So in a tree of thought prompting, suppose we are enumerating all possible paths, and finally we are deriving the final output. So now we can check. So like each path is giving a final output. Now we can check what is the, what is the majority output. Suppose you are getting 10 outputs, because there are 10 possible paths. Okay, in a tree there are 10 possible branches. So all these 10, when the LLM will be following a particular branch, it will derive an output. Now you are having 10 different outputs from 10 different branches. So what is the majority output of these 10 different branches? So that will be the self-consistency. It is an ensemble approach that samples multiple chains of thoughts from language models decoder. It then identifies the most consistent final answer by marginalizing these sample chains. Okay, so you have a prompt, you have a language model, and then you are following different branches, and finally you can see the majority vote of all these outputs. Now there is also a graph of thought. So graph of thought means from the prompt only you have to generate a graph like structure. So in a tree of thought we are generating, or we are decomposing the prompt into sub steps, and then we are generating a tree like structure. But now we have to generate a graph like structure. Okay, and then we have to finally derive the output. So this prompting technique tries to model the human thought processes not only as a chain but as a graph. Okay, so this is the here it is the only difference. You know the difference between tree and graph. Similarly here, in order to decompose the problem into sub problems, we'll be deriving a graph, not a tree. Like here you can see that this is one example. The word earthquake comes from the words earth and the quake. The word earth means round and the word quake means shake. So you can see that earthquake comes from earth and quake means ground and the shake. Bhaskar, okay, so hello, am I audible? Hello, am I audible?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am, you
Yes,
are
ma'am.
audible.
Yeah. So Bhaskar, are you there? So so basically I'll be continuing from 2 o'clock. So now I think we have some time because we started late. No, I think we started around 12:15. So now my student will basically show you some other parts of the generative AI technique. I have a meeting. So but I will again resume the session from 2 o'clock. Okay, or 2:15. But as we have some time now, I think another 15 minutes. So my student will now show you some other component of generative AI. Bhaskar, are you there?
Also, am I audible?